Okay, good evening. Good evening. Can you hear me? Good evening. Yeah. Fine, let's get started. Yesterday, we have seen the three configurations of BJT: common base, common emitter, and common collector, right? Now, there are so many ways of drawing these configurations, but if input is given at base and output is taken at collector with the emitter at the signal ground or ground, then uh, the configuration is set to be common emitter, and we have seen that only this configuration gives 180 degrees phase shift. But if you give input at emitter, output at collector, and the base is grounded, then the word common means a common terminal which is connected to ground. So if base is grounded, then it is common base amplifier. If input is given at base, output at emitter, and the collector is connected to VCC. VCC means it is also ground node for AC analysis. Then we call this as an emitter follower or common collector. And there are so many ways to draw these configurations, right? Now, suppose if you want to draw the three configurations on a self-bias circuit, the voltage divider bias circuit, then how will you draw? How to draw CB, CE, CC on a voltage divider bias. How to draw CB, CE, CC on a voltage divider bias, right? So the DC is common. The DC is voltage divider bias. And how you can build the three configurations. To draw a self bias or voltage divider bias, we need 4 resistors like this. Four resistors. And we know that this is R1, R2, RE, and RC. And why do we connect R1 and R2? So that this base potential is positive and the diode is on. If the diode is on, then the transistor can move from cutoff region to active region. So you want to build a CE amplifier, In a CE amplifier, input is given at base, output is taken at collector, and emitter has to be at common ground. So how are we going to connect the signal? Think about it. So here you have to connect the signal at the base. At the output, you have to at the collector node you can take the output, and the emitter node has to be grounded. So how are you going to build a common emitter amplifier on this biasing circuit? So on this biasing scheme, we are going to build a CE, CB and CC configuration. Now, when you want to give input, give it with a capacitor. When you want to take output, take it out with a capacitor, and you can ground the common terminal with a capacitor. Now, if you ask me what these capacitors will do, we will see, because if the base is at 4 volt, the emitter is at say 3.3, and the collector is at some 5.3 volt. We have done the first problem. Do you remember? Now, these three numbers should be protected. If you don't protect these numbers on the transistor, then the transistor can go to cutoff region, right? Base should always be at 4. Whether you connect a signal or don't connect a signal, it should be at 4 volt DC. Emitter should be at 3.3. Collector should be at 5.3. So what is that element which isolates the DC analysis and AC analysis and blocks these voltages? So we need a device, an element that can block DC, right? It has to store that DC. Blocking means what? Storing to that value and making it stay there, right? It should not vanish. It should stay there, right? So what do you mean by blocking money? So you have say you have so many expenses to do, but you block some money. Blocking means saving them, right? Blocking is not avoiding them. Blocking means saving them, right? So we need a device that can save these voltages, charge to these voltages. So what are those? What is that device? That's a capacitor. If you connect a capacitor at the input, then this guy is going to charge. This guy is going to charge to the 4 volt, whatever. And this guy is going to charge to that 3.3. And this guy is going to block or charge to that 5.3. So we need 3 capacitors, right? One at input, one at output, and one at the common terminal. So blindly, just go and connect 3 capacitors. That's it, right? Just go and connect 3 capacitors. So let's connect. Input is given at base. Output is taken at collector. And emitter has to be grounded. And emitter has to be grounded. Right? So this is a simple way of drawing a common emitter. So how do we draw a common emitter? First, draw self-bias. And we need 3 capacitors because the BJT has 3 terminals. And those 3 voltages, you have to somehow block them or protect them. If you don't save them, then the BJT can go to cutoff, right? What happens if you don't connect a capacitor and directly give V in here? If you directly give V in instead of 4 volts plus V in, if you don't charge that 4 volt and directly give V in at the base, then V in is a millivolt signal. When a millivolt signal is given to base, the transistor can go to what region? Cutoff region, is it not? So you have to, now what is the base potential now? It is 4 volt plus V in. The base potential is now 4 plus V in. So your 4 volt should be there, right? Whether if you open circuit the capacitor and remove the capacitor, you still have 4 volt. You connect the capacitor will charge to 4 volt. It's blocking them. It's blocking. Blocking means charging them, right? So it's always, or rather, from the transistor point of view, it has coupled that input. It has coupled the input with some DC, right? So some books even call this as a coupling capacitor, right? So the 4 volt, basically, whether you call it coupling capacitor, bypass capacitor, whatever name, don't forget the inherent behavior of a capacitor. Capacitor is meant to charge. Capacitor stores charge. Capacitor stores charge. Capacitor stores DC. Capacitor stores DC, right? So this is how we build a common emitter. We will talk about these capacitors later because now we have to connect, draw CE. Okay, this is a CE amplifier because the emitter is grounded. How do you build a CC amplifier? Common collector. Common collector. First, draw self-bias. self-bias. R1, R2, RE, and RC. And how do you build a common collector, CC amplifier? In a CC amplifier, input is given at base, output at emitter, collector has to be grounded. Collector has to be grounded. And the story is same. Protect these numbers in capacitors. So connect an input with a capacitor, take the output with a capacitor, and ground the common terminal with a capacitor, right? So this is how you draw a common collector amplifier on a self-biased circuit, right? But is it a good way of drawing? No, definitely bad. I told you, drawing a self-biased circuit is like going on a bullock cart, right? Those days are gone where we use capacitors in amplifiers. We should be shy of using capacitors on an amplifier because capacitors cannot be fabricated on an IC. So these circuits were till the 1960s, right? So once the op-amp was made somewhere in the late 1960s, in the early 70s, right? Then there was a hint that is when people got a hint that these what you call biasing structures are going to get outdated. But still people started using in discrete design. And now these days, everything is integrated. You ask, you will get an IC, right? So you name anything, you have an IC for it. And all these analog circuits have become outdated. Now, in those days, EDC was the subject, right? So now it's like microelectronics. So everything is at the micro level. These structures cannot be used at the micro level. So they are outdated. But because history, we have to know history. So that's the reason I'm spending 15-20 minutes time on these old circuits, right? So something like 1960s or 70s, it's if I'm right, they have started to get outdated when your parents were born, right? I think you probably I'm born in 74, so in the late 1960s, probably when in the early 70s, when your parents are born, at that point these structures, that there's a hint that all these are outdated, going to get outdated, because none of these structures can be built on an IC, right? So they are so old, right? But if you study some very old books, there they claim that these are excellent and these are, blah, blah, blah. But if you study new books, first of all, there are no such circuits in new books. They don't recommend these kind of, structures. But some students who study old papers of what you call GATE, if you see old papers of GATE, 10 years back and 15 years back, 20 years back, you will find so many questions on the voltage divider bias. Of late, last 4 or 5 years, if you see, there is no BJT, hardly one question or two question. Mostly it is on MOSFET. Are you getting, right? So these structures, if we solve old papers, then you will know all of them. Okay. So how do let's respect history, right? Because we have come from there. So how do you build a voltage divider bias common collector amplifier? How are you going to build? Input is given at base. So what sort of circuits are till today, from 60s till today? Differential amplifier pairs, level shifters, current mirrors. These are the foundation of analog. These are the foundation of analog. Input is given at base, right? Output is taken at emitter with a capacitor. And who has to be grounded? Collector. All of you, I told you what is VCC called. VCC called signal ground. VCC is called what ground? Signal ground. So you can, yesterday in the problem, there was no RC. So directly the collector, I've connected it to ground, right? So the signal ground. But if you need RC, then you need a bypass capacitor here. Because what is capacitor for AC analysis? It will act like short circuit. So the collector is directly connected to VCC. It's connected to the ground. Please, if I ask you what is this from AC point of view, what you should say? What is this? What is this? What is this? What is this? This is ground. 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 For what analysis? AC analysis. This is ground for AC analysis. collector is connected to ground. Capacitor will act like short circuit for AC. So collector is connected to ground, common collector. So this is how you build a common collector amplifier on what bias? On a self-bias circuit. Okay. So how do you build a common base amplifier? Common base amplifier, same story. First draw self-bias. Self-bias R1, R2, RE and RC. So this is a common base amplifier, common base. So where is input given? Input is given at emitter, output at collector, base is common, base is common. So how do you protect these voltages, right? So this is at 4 volt, this is at 3.3, this is at 5.3, you have to protect those numbers, right? So give the input with a capacitor, take the output with a capacitor, ground the common terminal with a capacitor, right? So let's connect. Input is given at emitter. Output is taken at collector. And the base terminal so this is going to get charged from the VCC to a value VCC R2 by R1 plus R2 by voltage division, right? So that is 4 volt. If this is 4 volt, you're going to get 3.3 here and 5.3. So 3.3 is charged by this capacitor and 5.3 here. Say common base amplifier, this is a CB amplifier. You have to block the 3 voltages in capacitors. So capacitor behavior everywhere is same because three capacitors to 3 terminals, right? So what is the purpose of these capacitors? Purpose of the capacitors. In amplifier, right? You can take a CA amplifier, standard. So what is the purpose of these capacitors, right? So we know that capacitor stores charge, is it not? Now, if you're a rich man, then the common emitter you can build like this. This is not self-bias because self-bias means the same VCC should be used for both, for the base current as well as the collector current. It should be used to switch on the BJT. But now I have given 4 volt here. If I give 4 volt, naturally I'm going to get 3.3 volt. 3.3 volt. You can charge this here, right? And this will be suppose 5.3 volt. Here you are taking the output. Am I right? So this is a problem yesterday we have done. But now what I'm saying is, how do I build a self-bias circuit? Self-bias in the sense, it should be self-sufficient. This 4 should come from the 10 volt. For the 4 to come from 10, I have to connect 2 resistors here, 2 resistors. And if your beta is large, you can have 6K and 4K here, right? 6K, 4K, 10 volt. So roughly this voltage, if you neglect the base current, you're going to get how much? 4 volt. This is going to be 3.3. If your current is, or if your resistance is 3.3K, this is 1 milliampere. If this is 1 milli here, and we have done a problem, right? This was 4.7K, this is 5.3 volt. So now we have 3 voltages, 4 volt, 3.3, 5.3. So how do I block them? How to block these voltages, right? So we have to protect these voltages. How do you block them? To block them, what I'm saying is, you can connect a capacitor like this first. If you connect it nicely, it is going to charge to 4 volt. And if you connect one more capacitor here, it's going to charge to how much? 3.3. And you can have a capacitor. If suppose I connect another load, what is this load? Load can be RL, or it can be the input resistance of next stage, right? So if you connect the second amplifier here, cascading, then nicely it is going to charge to how much? 5.3 volt. So suppose the voltage here, this voltage here, suppose this voltage here is 5.3 plus 0.4 sine omega t. This voltage here is 5.3 plus 0.4 sine omega t. The capacitor will charge to 5.3, and you are going to get only AC output, right? So in every in all the 3 capacitors, what are they doing? They're just charging. That's it. They are just charging, right? And every device will do. I mean, it's not just amplifier. If I have 5 volt, there's 1 kilo ohm. What is the voltage at this point here? The voltage at this point is 5. So the open circuited voltage is 5. So if you connect a capacitor, it will also charge to 5. So before connecting a capacitor, the voltage was 5. After connecting a capacitor, the voltage is still 5. It has blocked that voltage. It has blocked it. One more example. What if I connect a divider like this? This is 5 volt, 1K, 1K. Before connecting a capacitor, what is the voltage here? 2.5. If you connect a capacitor here, it will also be 2.5. Capacitor will always charge to the open circuited voltage. You just open circuit and see whatever the voltage is there, to that voltage the capacitor will charge. Now, if I open circuit this capacitor and see what is the voltage here across this 4K, 4 volt. Connect a capacitor, it will charge to 4 volt. Before connecting a capacitor, what is the voltage here? 3.3. Connect a capacitor, it will block that. Capacitor's main job is just to charge or block the potential difference. It will block to that open circuited voltage. Now, what is the extra thing I'm going to do here is, I am going to connect a signal here. That's the only difference here, signal. If you connect a signal, what will happen? This is 1 millivolt signal. So the capacitor is probably still charged to 4 volt only. But what is this voltage here? It is going to be 4 plus the small signal V. It is going to be 4 plus the small signal V, and this capacitor is going to act like short circuit for AC. That is the beauty of capacitor. It is going to act like the moment you connect a microphone and you start saying hello, hello like this. So the moment the signal is there, the complete signal will appear here, here as V. So you already have DC. So this is a diode. What is a diode small signal analysis we have done? A nonlinear diode is going to behave as linear if you give some DC and then you have to apply some small signal. Do you remember? Right? Of course, the diode takes a drop of 0.7, and you have another resistor here, 3.3K, across which you have the 3.3 volts here, right? So this is a diode here. So the voltage here is 4 plus V. So please don't forget, capacitor is going to store charge. It is going to what? Store charge. And why this is a big headache, this circuit is a big headache for me is, there is a big army here, right? Today we claim that 1 million transistors are in an active region and they have a single cell phone battery, right? So if there are any amplifiers in your cell phone, so many millions of amplifiers, they're all properly biased. They're all properly biased, and there are no resistors inside. There are no capacitors inside. Only transistors are there. Transistors are biasing transistors. That's the technology, the current mirror technology, right? So it is so excellent if you see, and it is simple also. Please, current mirror problems and differential amplifier problems, they are dead easy. Believe me, that voltage divider is a big headache because so much army is here. 6K, 4K, 3.3K, capacitors, DC analysis, AC, nothing. The moment you see a differential amplifier, minus GMRC, that's all. Any differential amplifier you take, you can take a half circuit and analyze it and write minus GMR. But this is not that simple. DC equivalent, AC equivalent, capacitor, open circuit for DC, short circuit is all big headache. When you study this, your mind gets blocked. You almost feel like, you have to leave electronics. Then finally, when you go inside, you have big structures, differential amplifier. They are so simple. They're so easy to analyze them. You'll just, play around. Here, one big army of resistors and capacitors are there. Imagine there are 10 transistors. For one transistor to maintain in active region, 4 resistors, 3 capacitors. Imagine if I have 10 transistors. 10 transistor means, what should I say? One bag full of resistors and capacitors you have to carry. Are you getting? So these are for discrete design. They cannot be used for integrated circuit design, right? Capacitors in the order of microfarad. What is the disadvantage? The disadvantage is capacitors in the order of microfarad range is difficult to fabricate. Difficult to fabricate. Hence, we go for direct coupled amplifiers. Direct coupled amplifier. This is the first statement I've used for op-amp. Op-amp is a high gain direct coupled amplifier, right? Capacitors cannot be used because the microfarad rate. See, imagine how much polysilicon will you pour on a wafer, right? 2 plates separated by dielectric, right? So you have to pour so much of polysilicon just to build one capacitor. In the place of that capacitor, you can fabricate 10,000 transistors in that space. Instead of making one capacitor, you don't mind making, it's much easier to build 10,000 transistors there, right? So please don't go for these kind of circuits, right? They're all outdated, right? Okay, capacitors in the order of microfarad range is difficult to fabricate, hence we go for direct coupled. Fine. And I'll tell you one more fun here is, can you imagine that whatever dynamics that occurs across 4K is the same dynamic across 6K? If suppose across 4K there's some signal pattern, right? There's some signal pattern going on. The same pattern is there at 6K. So it's not needed, right? Why? Because the 4K and 6K are going to be in parallel for AC analysis. The 4K and 6K are going to be in parallel for AC analysis. They are going to be in parallel for AC analysis. That's a big headache here. See here. Let me draw AC equivalent. So you'll get surprised. Capacitors should be replaced with short circuit. So when you draw AC, you will find that it's a shame on these voltage dividers, because these voltage dividers will come in parallel. They're going to affect the input resistance also. Nicely, they're going to come in parallel. See how trouble they create now. Here, there is a short, you have V in. there's a short here, and there's a short here, there's an RL here, and this is VCC, this is also ground, right? So VCC is replaced with short. It's all ground node. Now tell me how many nodes this circuit has. How many nodes this circuit has? How many nodes this are? Suppose this is node 1. This is node 1. No. What is a node? What is a node? A node is present at either end of the element, right? So there's no element, they're all at the same node. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, 2. This is 1, 3. So they're all at the same node, right? Now, let me redraw it. How to redraw? First, the best way is first draw the transistor. First draw the transistor and make the connections. This is at node 2, node 1 and node 3. Node 2, node 1 and node 3. One is directly connected to ground. Now, between 3 and 1, you have RC. Between 3 and 1, you have RL. Between 2 and 1, you have R2. Between 2 and 1, you have R1. And here we end. So see the headache here. The signal is not seeing the transistor first. The signal is like peeping. Where is my BJT? Where is my BJT? Because I'm seeing R1 and R2. This fellow is definitely going to affect the input resistance. So you can take this as a homework problem. Because right now we are going to start shortcuts, right? Directly we can tell the answer, but please don't do by shortcut method. Do by the small signal. Just replace the transistor by small signal and the small signal model. And here I want you to prove that the input resistance is R1 parallel with R2 parallel with the resistance between base and emitter is R5. This is R1. See, R1 parallel, R2 parallel, R5. What if you connect the same voltage divider, all of you see here, the same voltage divider for common collector? Yesterday we have seen common collector is giving 0.8 mega ohm, if I remember, 0.8 mega, almost 1 mega ohm it is giving. Imagine 1 mega ohm parallel with 2 kilo ohm, 3 kilo ohm, like that. 1 mega ohm parallel with 2 kilo ohm and 3 kilo ohm. What will happen if a mega ohm comes in parallel with a kilo ohm? This is nonsense, right? So I would probably call this as it's a shame. It's a shame on voltage dividers. Voltage dividers to affect the input resistance RN. So the input resistance is gone because of, see, voltage divider's job is only to bias the BJT. So you nicely put these two resistors, for biasing, and suddenly the whole story changes for AC analysis. In AC analysis, these resistors, they simply come in parallel. They're going to affect the input resistance, right? So this is terrible. So RN is this, and a resistor in parallel to a voltage source has no meaning. So your voltage gain, I want you to prove it is still, yesterday we have done this, minus GM into RC. Oh, now RL has come, RC parallel RL. RC parallel. And what is the output resistance here? R0. For finding output resistance, load should not be considered. Your R0 is going to be RC. So please do this as a homework. We'll do it by shortcut now, but still, I want you to, take the transistor, replace the transistor with the small signal model, and solve this, right? And current gain, I don't want to calculate current gain, because my current is getting divided everywhere, right? This is I in. Now, R1 will say, I also need current. R2 will say, I also need current. The base current is going to be small. And this IC is now divided into two parts. So that's very terrible. These voltage dividers are hopeless, right? They affect your input resistance. They are even affecting your gain, right? Okay. So capacitors, yeah. I remember writing all the theoretical points, right? So what is the purpose of Purpose of input capacitor. Tell me, what is the purpose of an input capacitor, right? It is to couple V in. It is to couple the V in, right? Or clamp V in. It is to couple V in with a DC of VCC R2 by R1 plus R2, such that the transistor is in active region. That is why R1 and R2 are also called biasing resistors. Right? So I mean, as a student, we spent a lot of time, discussing with friends that capacitor behavior is same. Why in the textbook they are, naming them as coupling capacitor, bypass capacitor, like that? It's not because of the function of the capacitor. It's because where the capacitor is placed. The capacitor everywhere is charging, but it is placed at V in, and the DC is added, so it's called coupling. It's coupling the input. And look at the second capacitor here. They call it bypass capacitor, right? This is called bypass C. The emitter capacitor is C, bypass capacitor, and this guy is the blocking capacitor, right? So what is the purpose of bypass capacitor? The emitter capacitor. What the capacitor will do? Now we have to write all these theoretical points, when in university exams, you remember. So we used to write, all stories, right? And CE acts as open circuit for DC, and CE acts as short circuit for AC. Now you might say, so what, right? If it acts as open circuit for DC, then what is he doing? When CE acts as open circuit for DC, it allows the emitter resistor RE to stabilize IC/DC, because RE should be there. I told you, without RE there is no circuit. But CE acts as short circuit for AC. Okay, so what will he do? It eliminates RE because RE reduces gain, right? So that means what? We want RE for DC, but we don't want RE for AC. So who is that device which is saying that RE, you stay there for DC, RE, I'm going to remove you for AC, right? So the capacitor is very cleverly connected across RE. It'll act like open circuit for DC. It says, RE, just go and do your job. Stabilize IC/DC, fix the operating point. The moment the signal is applied, they say, RE, please, no, we don't want you, because I want large signal swing. So the gain should be there. If you are there, you will reduce the gain. So capacitor acts as short circuit for AC. It eliminates RE because RE reduces the gain, right? And of course, what is the purpose of the output capacitor? After the final amplification is done, we say that, sorry, we don't want DC. So we eliminate, so if you don't want DC, what do? We just eliminate that DC and we get only AC, right? Purpose of output capacitor, right? So one statement, it is to block DC and allow AC. It is to block DC and allow AC signal, right? And the gain calculation we will see, is it not? The gain calculation, we are going to see if RE is there, simple. RE will come in the denominator. When you take the input loop KVL, the extra thing is going to come 1 by GM plus RE will come, right? So obviously the gain is going to reduce. Without RE, it is R minus GMRC. So without RE, it is going to be RC by 1 by GM. With RE, I'll show you, it is RC by 1 by GM and extra resistor in series, 1 by R. So naturally, because of that extra resistor in the input loop, the gain is going to reduce, right? We will see how to calculate gain for different circuits. Okay, so let's come back here. Yeah, where did we stop yesterday? Yesterday I told you that today we are going to see how to shortcuts, right? So how the moment you see a circuit, how are you going to assess the gain of the amplifier just by inspection? For that, I have given you few rules. I call them as the resistance reflection rule. Resistance reflection rule. It's a simple rule, right? Very easy to remember. So I told you, if I am seeing through base terminal, suppose this is node 1, I am seeing here, and at this point, at this node 1, the BJT is connected, and I want to remove the whole BJT. I want to remove the whole BJT and connect a resistor. What will I connect? If I apply a voltage V here, and I pass this current I, the V by I is going to be R. So what R are you going to replace? Right? So just remove the transistor and replace a resistor R pi. This is a rule 1. But what happens if we have an extra resistor R here? And now I want to remove the transistor. To remove the transistor, we have to connect R pi plus, here, so here there's an R pi plus R. But through this R, 1 plus beta times of I is flowing. This I, this is going to be 1 plus beta times of I. So R pi plus 1 plus beta times of R, you have to connect. So if you go from base to emitter, there's a multiplication factor of 1 plus beta. There's a multiplication factor of 1 plus beta. This is rule 2, right? This is rule 1, rule 2. And what is rule 3? Rule 3, I said that this time your V by I, your I is going to be large. Your I is going to be large, right? 1 plus beta times large than this. As compared with rule 1, rule 3 is going to have a current that is 1 plus beta times larger. So naturally, Ohm's law says that R equal to V by I, R equal to V by I. If the denominator increases, if I increases, then the resistance is going to reduce, right? So suppose this is node 1. You can replace at 1, you just remove the whole transistor and you can connect a resistor. What is the value that you're going to connect? That value is going to be the same R pi, but divided by 1 plus beta, because the current is 1 plus beta times more. So R pi by 1 plus beta, it is alpha by GM. It is alpha by GM. You can take 1 by GM. Generally, I say 1 by GM, but alpha is 0.99. Some students are complaining, sir, small signal model, we are getting 24.567. But in your model shortcut, we are not getting 24.567. We are getting 24.587 like that. Then I say, okay, you want still more accuracy, then the alpha value, I have taken 1. Now I'm not going to take 1. Let it be alpha by GM, right? So if alpha by GM is nothing but R pi divided by 1 plus beta. What is alpha for MOSFET? For MOSFET, alpha is 1. Alpha means it's the ratio between the collector current and emitter current. There is no collector current, emitter current in MOSFET, only one current. So directly this answer will be the MOSFET answer if you put alpha 1, right? What is rule 4? Rule 4 says that if you have a resistor at the base terminal, Now you're going from emitter to base. You're going from emitter to base. Then what is this resistance? This node 1. At this, from node 1 to ground, you're going to connect a resistor. What resistor will you connect? Now you're going from emitter to base. So it is alpha by Gm. And that resistor R has to be divided by 1 plus beta. Because current is more, resistance is less. Here current is less, the resistance is more when you inject that current. So here there is a multiplication factor of 1 plus beta times. Here there is a division of 1 plus beta times. Alpha by Gm plus R divided by 1 plus beta. This is rule 4, right? So these are the 4 rules I have given you. One extra rule also, if you want, you can have. This rule 5 says that if somebody has given you a diode, and whether you see through base terminal, the current is going to be IB plus IC. Whether you see through emitter terminal, whether you see here, it is IE, or whether you see here, it is the same. Everywhere it is same. The current now is the addition of base current and emitter current, right? So in such an occasion, what is the resistance? This resistance is 1 by Gm parallel with R pi. The resistance is 1 by Gm parallel with R pi, provided there is a short between collector and base. Please, there should not be a short between base and emitter, only base and collector. Then any node you see, you're going to have the same resistance, right? So what is the proof for this? This is the small signal model. Here there is R pi, and here you have GMVB. This is VB. GMVB, VB. Now, base and collector terminals are shorted. Now you have to calculate resistance. When you want to calculate resistance, you apply a voltage V and find current I. All right? Current I. Now tell me, if V and VB are same, what is I? Your V is nothing but VB. Your I is nothing but VB by R pi plus GMVB. So your V by I is going to be 1 by R pi plus GM. This is like 1 by GM parallel with R pi. 1 by GM parallel with R pi. Of course, this value is also alpha by GM only, because you are seeing through emitter. But let us keep it 1 by GM parallel with R pi, right? For a reason I'll tell you later, because MOSFET answer also will become easy. Or you can do orally also. Orally, just tell me, what is the resistance given by current source? Orally, what is the resistance given by current source? If voltage is VB, current is GMVB. What is the resistance offered by current source? VB by GMVB, 1 by GM. So 1 by GM is in parallel with R pi, no? Yes or no? The current source, current is how much? GMVB. What is the voltage? VB. VB by GMVB. 1 by GM is the resistance offered by the current source, parallel with R pi. 1 by GM parallel with R pi, right? So this is rule 5. So let me repeat all the rules now. Just go through the rules. So base terminal, it is R pi. If there is a resistor at emitter and you're seeing through base, R pi plus 1 plus beta times of R. If you're seeing through emitter, it is alpha by GM. If there is a resistor at the base terminal, then it is alpha by GM plus R divided by 1 plus beta, right? And if you have a diode, then it is 1 by GM parallel with R pi. Okay. Calculate RN. Calculate RN. Calculate RN. And once we are done with all these rules, the last thing we have to include is early effect. We have to include early effect also, right? Okay. So I'll change the page now. I think you would have known the answer. I'll do it. Okay. Now, the beauty of this analysis is you will solve circuits which you have never seen till now very comfortably, and you don't know the operation of them, still you can solve. For example, a simple example is, we have not started differential amplifier yet. Differential amplifier is after all this CBCECs. But still you can find the input resistance Rn with this technique, right? Slowly we will go, right? You will understand one by one, slowly we will improve upon, right? See, I challenge you and say that you cannot solve these circuits, some of the circuits by small signal. It's difficult, but just by inspection, you can solve them with this technique, with this technique. Okay, so we'll come back to the first one here. Okay, so let's get started. And this is our first rule. What is the first rule? I'll name the node here, node 1. If I connect a voltage source V and inject a current I, what is the name of the terminal? The name of the terminal is enough here. Are you getting? Whether it is NPN or PNP, it doesn't matter. What is the name of the terminal? The name of the terminal is base. When the name of the terminal is base, emitter current will not flow, collector current will not flow, base current only will flow. Why base current will flow? Because the name of the terminal is base. Yes or no? So if you know that it is a base terminal, and then definitely you know that there is a base current. So when you apply V and there is an IB, V by I or VB by IB, your VB here by IB is going to be R pi, right? So from that node 1 to ground, you're going to have a resistance of what? R pi, right? R pi is going to be the input resistance as seen by this source. So who is seeing this? The source is seeing, right? The source is seeing, right? So now you can remove the whole transistor and connect R pi. So the whole resistance at this point from 1 to ground is going to be R pi. Now what about here? Again, I'll name 1 here. Again, I'll name 1. Now I want to cut this and remove the whole transistor circuit. How do I remove it? This is already R1 and R2, and this is node 1. Now I want to remove the whole transistor and connect a resistor from node 1 to ground. So here also, you're seeing through base terminal here, this resistance is going to Rx. The resistance Rx is here is going to be R pi. Now, what is the overall resistance here? The overall resistance. We know that R2 and R pi both are in parallel. R2 and R pi both are in parallel. When R2 and R pi are in parallel, then the combination is again in series with R1. So what is your Rin? It is R2 parallel with R pi plus R1. It is R2 parallel with R pi, right? So this is equivalent to an R1 here and another resistor which is R2 parallel with R pi. Now these two are in series. These two are in series, so you can add them. You can add. You can add. Similarly, I told you this is ground for what analysis? AC analysis. So R1 and R2 are going to come in parallel. This is R2 connected to ground. For AC analysis, VCC is also ground. So here you are going to have R1. And this is the BJT circuit. This ground. So R1 and R2 are in parallel. Here again you have R pi. So it is R1, R2, and then an R pi here. So what is the overall resistance here? The overall resistance Rn is going to be R1 parallel with R2 parallel with R pi. R1 parallel with R2 parallel with R pi. Are you getting? So now in this technique, we are going to convert transistors into resistors. We are going to convert transistors into resistors. So what is Rn in the first case? Rn is going to be R pi. Rn is going to be R pi. Rn is this. Okay. So what about rule 4? Rule 4. We'll go to the next page now. What about rule 4? Now at this node, what is the name of the terminal? The name of the terminal is the base terminal. In base terminal, emitter current will not flow, collector current will not flow, base current will flow. The base current is chota current. Chota current matlab bada resistance, small current, big resistance, big current, small resistance. Ohm's law, R equal to V by I. R equal to V by I. If the resistance is, if the current is small, resistance will be big. If the current is big, the resistance will be small. So here I'm going to inject a base current. So naturally, the source is going to experience big resistance now. What is the resistance value? The resistance value is going to be between base and emitter, it is R pi. And if you go from base to emitter, the multiplication factor is going to be 1 plus beta times. So the rule 2 says that, if you go from base to emitter, the multiplication factor is going to be 1 plus beta. Is it not? Or if you want, you can apply KVL. This is V and I. I is nothing but IB. Here you have VB, right? VB. And here there is I, right? So what is V? V equal to VB plus IR. VB plus IR. I is nothing but IB. I is nothing but IB. So what is V by I? V by I is VB by IB is R pi. IE by IB is 1 plus beta times of I. So if you want, you can apply KVL round the loop. You realize that your V by I is going to be 1 plus beta. What is IE by IB? IE by IB is going to be 1 plus beta times, right? So whenever you go from base to emitter, you simply multiply the factor 1 plus beta. This is the proof for this, right? Now, this RB has come in series, is it not? It has come in series here. The extra resistance has come in series. So what is Rin now? It is going to be RB plus the whole resistance here. What is the resistance from here to here? It is R pi plus 1 plus beta times of R. It is RB plus R pi plus 1 plus beta times of RE, right? So they are all in series. The resistance from here to ground is R pi plus 1 plus beta times of RE. There's an extra RB coming in the series. And in this KVL, can you see in this KVL? You'll have one extra IB RB. You'll have one extra IB RB if you write KVL round this loop, V by I, right? So this way you can avoid the small signal model. Yeah. Now what about this circuit? This circuit is, here you have RS and R1 and R2 are in parallel. R1 and R2 are in parallel. And here you have this RE resistance. Now what is the resistance Rx here? Rx. This resistance Rx is R pi plus 1 plus beta times of R. Am I right? See, please, you have to repeat. At least when I'm in the class, I'll make students shout, right? So R pi plus 1 plus beta times of RE, R pi plus 1 plus beta. You have to repeat that because you're sitting at home. I can't help you because I can't even see your face, right? Please repeat that. R pi plus 1 plus beta times of RE, R pi plus 1 plus beta times of RE. That is Rx. So now you have Rs, R1, R2, and what is the resistance from the node 1 to ground? It is Rx. So what is input resistance Rin? These three resistors are in what? Parallel, and the combination is in series. So it is Rs plus R1 parallel R2 parallel Rx. Rs plus R1 parallel R2 parallel Rx. And what is Rx? Rx is R pi plus 1 plus beta times of Re. R pi plus 1 plus beta times of Re. So this is ground for AC analysis. From here to ground, R1. So R1 is going to come in parallel with R2. R1 is going to come in parallel with R2. Okay. Now, all of you, what is rule 5? Rule 5 says that you can treat this whole thing as a load, and this is a diode. In future, this is going to be a diode, and at any terminal you see, there is a summation of IB plus IC, which is IE. So this you can always replace by a factor 1 by GM parallel with R pi. It is 1 by GM parallel with what? R pi, which is equal to alpha by GM only. Right? So let me replace it like this. So rule 5 is this is 1 by GM parallel with R pi. And now you want to calculate the input resistance Rin. Tell me what is Rin? Now transistors are going to get converted into resistors. So you're seeing through base terminal, you go from base to emitter, there is a multiplication factor of 1 plus beta. So it is R pi plus, or R pi 1, this is GM2 you can take, right? This Q1 and Q2, just to differentiate. R pi 1 plus 1 plus beta times of 1 by GM2 parallel with R pi 2. So there is no need of the small signal model intuitive. So slowly we have to develop this intuition, right? Base terminal, chota current, IB, right? R pi. Emitter, bada current, chota resistance, alpha by GM. If you see through emitter, it is alpha by GM. If you see through base, it is R pi. So you have to tell in your mind, right? Emitter means big current, small resistance, alpha by GM, right? Because what is the relationship between R pi and GM? R pi is beta by GM. What is R pi? Beta by GM. Beta by GM is R pi, right? Okay, now we shifted from base to emitter. Now we are going to shift from base to emitter. Please, all of you, it is not a rule that you have to do by this shortcut. In the exam, if you have an element of doubt in this analysis, what is there? An extra 1 or 2 minutes you are going to spend. So please replace transistor by small signal model and apply Kirchhoff's laws. Please, you have to do it. Are you getting that? These are all techniques, right, which will save time. If you are not interested, you can always do by Kirchhoff's law, right? And solve the problem. That is why in the material, right, the volume 2 is written by me. So volume 2, I have given questions, but I have solved by normal method, right? The complete volume 2 normal method. It's not like RPy. Here we can discuss, but in the material, it's kind of difficult, right? So it's like perfect, proper Kirchhoff's laws. I've solved volume 2, right? So you can solve by that method. This is intuitively. It's like by looking at the problem, we are knowing the type of filter is something like that, right? Now tell me, what is IN? Let me put node 1 here. And here I'm connecting a voltage V and current I. This time, what is I? I is IE. This time, what is I? I is IE. Is it not? IE, we are injecting. And your V. And what is RIN? If you see through emitter, your RIN is going to be alpha by GM. Your RIN is going to be alpha by GM. So what is the proof for this? What is the proof for this? This is nothing but your VB. All right. And here you have IE here, right? So your I here, I is going to be minus IE. And V is going to be minus VB. So what is VB by, V by I? V by I is R, right? VB by IE. VB by IE is alpha by GM. It is VB by IE. Alpha by GM, right? What is VB? What is VB in all the three forms? What is VB in all the three forms? Let me write VB in all the three forms for your convenience. Do I have space here? Yeah, tell me what is VB in all the three forms? VB, we know that it is IB into RPy. It is IB into RPy. But what is RPy? RPy is beta by GM. RPy is beta by GM. It is IB into beta by GM. So what is beta times of IB? IC. IC into 1 by GM. IC into 1 by GM, right? Or what is VB? VB is IC into 1 by GM. Or VB is IE into alpha by GM. Because IC by IE is alpha. So I'm giving you three forms for VB. Three forms. VB is IB into RPy. VB is IC into 1 by GM. And VB is IE into alpha by GM. Okay. So what is a blind rule here? No proof, nothing. If you see through emitter terminal, it's alpha by GM. That's it. Now let me put node 1 here. Let me put node 1 here. Node 1. This is my answer here. My answer. Yeah. Let me put node 1. All of you, I want to cut this whole amplifier right side because I'm looking through left here. Complete amplifier I want to cut. So can you suggest me what should I do? Right. So this complete amplifier, I want to calculate R in here. But it so happens that this guy is connected here at node 1. So I want to remove this whole thing and I have to put some resistance Rx. So what is Rx from node 1 to ground? From that point to ground, what is Rx? You're seeing through emitter. If you're seeing through emitter, then this resistance is going to be alpha by GM. Alpha by GM. So a transistor is gone, right? Don't disturb this guy because you're finding through base terminal. The other section you just remove and calculate, right? Alpha by GM. Now, if you go from base to emitter, what is the multiplication factor? It is RPy plus 1 plus beta times of alpha by GM. So what is alpha into 1 plus beta? What is alpha into 1 plus? Alpha is beta by beta plus 1. Alpha is beta by beta plus 1. Your alpha is going to be beta by beta plus 1. So what is beta by GM? It is RPy plus alpha is beta by beta plus 1. So it is beta by GM. Beta by GM is again RPy. R pi plus R pi, it is 2 R pi. See, any book will tell you that a differential amplifier will give you 2 R pi, but we have not started differential amplifiers yet, but still we come to a conclusion, right? Because the right side amplifier, I just cut, I removed it. So from where did I get this motivation that I have to remove the right side? Who told me that I have to remove the right side, right? Who told me that I have to remove the right side? The biggest motivation is this type of network, right? This type of network. So when you have a network like this and you want to find here, what do? We always come from here. From here, we just remove this guy. Suppose this is 5 ohms, 5 ohms, 10 ohms, 3 ohms. So what do? So this will be 3 ohms. This will be 10 ohms. And then this 2 resistors we have to replace by a single resistor. This is node 1 to ground. From node 1 to ground, the 5 plus 5 is going to be 10. 5 plus 5 is going to be 10. 10 parallel 10. 10 parallel 10 is going to be 5. 5 plus 3 is going to be 8. Is going to be 8. So the biggest motivation is this. So if I have a transistor here, if I have a transistor, I would be doing the same thing, right? So if I have a transistor here, I just remove it and put an R pi here. Or if I have a transistor like this, I would just remove this guy. And instead of 5 plus 5, 10, I'm going to remove here and put alpha by GM from that point to the ground node. Are you getting? So the biggest motivation is these simple resistive networks, right? So when we can do equivalent resistance for a resistive network, why is that we are going for the small signal model and applying by Kirchhoff's law? We can even convert transistors into resistors if you, yeah. Okay. Now, yesterday I told you, I calculated the time for one circuit in small signal model. We have taken almost half an hour, right? So it's been around 15 minutes and we have completed the 9th problem, right? And if practice is there, probably you'll do each problem in half a minute or maybe even less than that, right? If you practice. Okay. Now tell me, how do we solve this? Because I want to come from here like 2 ohms and 3 ohms, and here you have 5 ohms like that. I'll put node 1 first. I want to cut this whole fellow and connect a resistor from here to ground. So what resistance will I connect here? This has to be alpha by GM. So this alpha by GM, this is R parallel with alpha by GM. What is Rn? Now the rule 4 says that if you have a base resistance and you're seeing through emitter, if you have a base resistance and you're seeing through emitter, then it is going to be alpha by GM plus that resistance R parallel with alpha by GM divided by 1 plus beta. So the rule 4 says that if you have a base resistance, then that resistance should be divided by 1 plus beta. That resistance should be divided by 1 plus beta. So first you remove this guy here, and there is an alpha by GM here, right? So it's, or you can treat this as R here, and here there's an extra resistor, alpha by GM. And how are these two? They are in parallel, so you can make them 1. So it's alpha by GM plus that resistance divided by 1 plus beta. And now tell me, Where should I put that node 1 and from there to ground? I'll take this point, right? And I want to cut this whole transistor and replace it with a resistor from here to ground, right? So what is the resistance from seen through base terminal? The resistance seen through base terminal, this is going to be R pi, am I right? So this is node 1 to ground, this is R pi. So what is Rn now? Rn is going to be R pi plus, you're going from base to emitter, there is a multiplication factor of 1 plus beta. R pi plus 1 plus beta times of R pi. It is R pi plus 1 plus beta times of R pi. So wherever you want to cut that network, you can make it node 1, right? Wherever you want, just you want to cut the network, you can make it. See, I'm seeing through the base of this terminal. I'm seeing through base of this terminal. What will you do? This transistor you leave, other part, whatever is left, that there you can name that node and then cut that fellow and connect a resistor, right? A student is asking, what is the limitation of this method? See, the only limitation of this method is it saves time, right? It terribly saves your time. That's the biggest limitation. Okay. So if you want to save time, you can always do by this method, right? So it's good. Actually, it's fun, when you're doing it, because you're not drawing anything, right? You're not doing anything. Just by inspection, you're telling the answer. No small signal, nothing, right? So this is node 1. So from node 1 to ground, I want to connect a resistor Rx. So what will you connect? This guy is going to be this is node 1. From node 1 to ground, you can have a R pi plus 1 plus beta times of R2. And how are these two? How is R1 and this, both are in series. Then what is your Rin, the total Rin? It is going to be R pi plus 1 plus beta times of the resistor at emitter. So what is the resistance at emitter? These two are in series, so it is R1 plus R pi plus 1 plus beta times of R2, right? Okay. See, it's simple, sir. I'll tell you, a BJT has got 3 resistors at 3 terminals, right? It's got 3 resistors at 3 terminals and 3 multiplication factors, right? If you see through base terminal, it's got R pi. If you see through emitter terminal, alpha by GM, and there is an early effect, collector terminal is R0. So how will you connect one BJT with the other BJT? There are 3 ways of connecting one BJT with the other BJT. You connect them either to the base terminal, you connect them either to the emitter terminal, you connect them either to the collector terminal. And if you know what is the name of the terminal, if you know that this is base, whether it's NPN or PNP, doesn't matter, it's base, and you want to remove the connection, you want to just take the scissors and cut that connection, what you have to do? Node 1. The day I put node 1, that means what? I'm just going to remove that transistor and connect a resistor from there to ground. So if I want to remove that transistor, you should first know what is the name of the terminal. That is enough. What is there? You know that this is base, right? So if you know it's base, it's R pi. If there are 2 transistors connected and the connection is at the emitter and you want to cut the connection and remove that guy, the remove. So when you want to remove it, you should know the name of the terminal. The name is emitter alpha by GM. Two transistors are there. They are connected at the collector terminal. The Q2 is connected at the collector terminal. I want to cut and remove, put R0. That's it. Are you getting? So it's quite simple. Just for this, the name is enough. The name. You should know that transistor has 3 terminals, and you should know the names of them and the value of resistances. If you know the value of resistance, then that's it, right? So the only resistance I have forgotten now, the early effect. We are going to include that in a short while, after some time, right? It's just R0. We're going to include R0 later, but now slowly, we are going slowly. 2 terminals have taken base to emitter, emitter to base, base to emitter, emitter to base. Slowly, I'm going to include what? Collector also, to avoid confusion. If you ask me, sir, why you didn't include early effect? First of all, most of the gate problems, there is no early effect. If you want to include early effect, why in the first problem itself, right? Now we are still thinking, our mind is thinking about base emitter, base emitter, base emitter. Base matlab R pi, emitter means alpha by GM. So once this is done, I'll go for early effect also, the collector terminal, right? So if you want, you can take the screenshot, right? Is the notes, are you getting the notes? The whole lecture notes, are you getting the whole lecture notes? Yeah. Good. So now we have calculated the input resistance and the resistance seen through emitter and the resistance seen through base terminal. And the last parameter is the voltage gain. Current, I told you, current gain is not at all a parameter. If your input is at base, output is at emitter, 1 plus beta. Input at base, output at collector, it is beta times, right? So what about voltage gain? For voltage gain, just tell me, what is voltage gain? AV is V naught by V, V naught by V. Now, how can I have the ratio of voltages equal to the ratio of resistors? I want to have resistors, suppose this is RA and RB. I want to have V naught by V in directly as RA by RB. When can I have the ratio of voltages as the ratio of resistors? Provided the numerator current and the denominator current are same. The numerator current and the denominator current are what? Same. Now, if you ask me, what is the numerator current and what is the denominator current? You have 3 ways of writing. One is numerator current can be IB, denominator can be IB, and both get cancelled. Numerator can be IE, denominator can be IE, and both get cancelled. Numerator can be IC, denominator can be IC, both get cancelled. Then the ratio of voltages can be the ratio of resistors. So by seeing a circuit, somebody asks you voltage gain, resistors divided by resistance, that's it. But I like numerator as collector and denominator as collector. Why? 3 ways are there. I'll give you all the 3 ways. But the first 2 ways I'm not going to use. I will teach you, but I will make you practice the 3rd way, which is the collector. Why? The reason is MOSFET has only collector current or drain current. If you have practiced for numerator collector, denominator collector current and directly write the answer, same answer is MOSFET. The same answer, it is going to be for MOSFET. MOSFET is not going to be any different from BJT. The moment you find a circuit, in fact, I'll tell you, you'll be bored when you're writing MOSFET because you almost feel that you're writing the same thing what is there in the BJT and your answers are not changing, right? So for voltage gain, I'm going to give you voltage gain now, and the ratio of voltages is the ratio of resistors. Numerator, a bunch of resistor, denominator, a bunch of resistor, that's it. Resistance by resistance is voltage. Everything we are going to convert it into resistors now, right? Voltage gain. Please have patience. The first two methods, I'm not going to use them, however, right? So voltage gain, and I tell you, what are the three ways of writing VB? VB. I like VB to be called as, IC into 1 by GM. I like 1 by GM multiplication. But if you say that, no, IB into R pi or IE into alpha by GM, right? So the VB portion can be written as three ways, right? Okay. So let me give you the three ways now. Shall I take a fresh page for this so that you see all the, there's no deficit of pages here. We'll take a fresh page here so that all the three you can have in the single page. VCC is ground for AC analysis. Here there is IE, here there is IB, and here you have VB. Am I right? Now, what is the voltage gain? V0 by V. What is V0? V0 is going to be minus ICRC. Why minus? What is IC? IC is 0 minus V0 by RC. What is IC? IC is 0 minus V0 by RC. So V0 is minus ICRC. We know that common emitter amplifier gives 180 degrees phase shift. What do you mean by common emitter? What do you mean by common emitter? It is not that emitter is grounded. It is input at base, output at collector. If input is given at base, output at collector, you are going to get a negative sign, right? You're going to get a negative sign. If emitter is grounded, okay, you get more gain. If emitter is not grounded, then you get less gain. But for 180 degrees phase shift, input should be given at base, output at collector. Okay. What is V in? What is V in this loop? Tell me. It is IB into RB plus VB plus IE into R. IB into RB plus VB plus IE into R. Now, first in terms of IB. In terms of IB, I am going to write numerator and denominator. So what is V0 by V? V0 by V in is going to be minus IB into 1 plus beta times of RC by IB into RB plus R pi plus 1 plus beta times of R. And of course, IB gets cancelled, and this is your V0 by V. Now just tell me, what is this RB plus R pi plus 1 plus beta times of RE? What is RB plus R pi plus 1 plus beta times of RE? What is this? This is the resistance at the base terminal, resistance at base. And because RC is at collector, 1 plus beta times of, sorry, what is the IC? IC is what? IC is beta times of IB. It is beta times of resistance at collector divided by resistance at base. So this is one formula, but we don't use it. The moment somebody gives you a circuit, what is voltage gain? Beta times of the collector resistance divided by the resistance at base, right? So when you take V in IB, RB, what is VB in terms of IB? What is VB in terms of IB? VB is nothing but IB into R pi. So I'm putting R pi here, and IE is 1 plus beta times of RE. So this is nothing but the resistance at base. Beta times of collector resistance by resistance at the base. So this we are not going to follow, okay? In terms of IE, what is V0 by V? So you do V0 by V in, this is equation 1 by equation 2. This is equation 1 by equation 2. What is V naught by V? Tell me. It is minus of now IE, right? By IE. IE gets cancelled. So here I'm going to write alpha times of the collector resistance by Re plus alpha by Gm plus Rb by 1 plus beta. All of you, what is this resistance? Tell me. Alpha by Gm plus Rb by 1 plus beta. Alpha by Gm plus Rb by 1. That is nothing but the resistance seen at what terminal? Emitter. So what is the formula we are going to do? Alpha times of collector resistance by resistance at emitter. This also I am not going to follow. Okay. So some students say, sir, I want in terms of this. Okay. So three ways you can write. In terms of IB, I'm not writing. In terms of IE, I don't write. In terms of IC, I will write. In terms of IC. Why I like in terms of IC is because I don't want to use my brain. I don't want to use my brain. I just want to write resistors. That's it. What are the resistors in the output? See here, look at my finger here. So I just put my finger at collector to ground. Who is the resistor at collector? RC. Who is the resistance at the input side? Who is the resistance at the input side? RB is there, VB is there, which is 1 by Gm, plus RE is there. So I will just write resistors in the numerator and in the denominator. Denominator is input loop. See here, this is denominator. Denominator. This resistance for output is at the numerator. This is numerator. So in denominator, I'll write resistors everywhere, right? Now, if there is an emitter resistor, I'll divide by alpha. Base resistance, I'll divide by beta. So you know why I'm doing it. Because this tells me a simple relationship between emitter current and base current. All the base resistance by beta, all the emitter resistance by alpha. Can't you do it? And wherever VB is there, just write 1 by Gm. The moment, because when you go for MOSFET, what will happen if you go for MOSFET? Alpha is 1 and beta is infinite. So you don't get this factor, alpha is 1 and beta is infinite. So you remove this factor, it becomes what you call a MOSFET device. Are you getting, right? So I will follow this because this is in terms of IC. This is in term, I like this. I just write resistors in the input loop. Emitter resistors, what is the rule I am following? Emitter resistors divide by alpha. Divide by alpha. Base resistors divide by beta. Divide by beta. Please don't divide anything with the collector resistor because we are writing in terms of IC. Numerator is IC, denominator is IC. These two resistors, one you divide by alpha and the other one you divide by beta. And this also is simple, right? The second one also I like. It is collector resistance by resistance seen through emitter terminal, right? Alpha by Gm plus Rb divided by 1 plus beta plus Re. Okay? Or you can simply write all the resistors and wherever VB is there, just write 1 by Gm in the place of VB and emitter resistor divide by alpha and base resistor you divide by beta, right? Just tell me which one do you like? Which one do you like? Which one do you like? So we are trying to make the current as same, the numerator current and the denominator current as same. And please don't forget the negative sign, right? So don't forget the negative sign because common emitter is going to give 180 degrees phase shift, right? So your wish, I think you know even this, Rb plus Rpi plus 1 plus beta times of Re, that is the resistance at base. Or what is the resistance at emitter? It is alpha by Gm plus Rb by 1 plus beta plus Re. But I like this, I just write and emitter resistors you divide by alpha and base resistors you divide by beta, right? That also you can do. Now alpha, please don't forget, what is alpha? Alpha is nothing but IC by IE, which is beta by beta plus 1. Alpha is nothing but IC by IE, which is beta by beta plus 1, and beta is nothing but IC by IB. Beta is nothing but IC by IB. Alpha is IC by IE. The typical value of alpha is around 0.9999. IC by IE. Numerator is small, denominator is large. So you almost get 0.99 like that, right? Alpha is almost 1. Generally, I used to neglect alpha and do 1. Some students are complaining. They are saying, sir, thoda decimal, some mismatch is there. Okay, if you want more accuracy, then please divide emitter resistance by alpha and base resistance by beta. Whatever answer the small signal model is going to give you, pakka same answer you're going to get here, right? It's going to get here. Okay, calculate the voltage gain. Please, we are writing in terms of what? IC. So wherever VB comes, please, wherever VB comes, what you have to write? 1 by GM. The moment VB is there, please don't write R pi or alpha by GM. Why you should not write R pi? Because our numerator current and denominator current is what? IC. Please don't write R pi for VB. Don't write alpha by GM. 1 by GM. Simply 1 by GM. Because for MOSFET also it is 1 by GM. 1 by GM. 1 by GM you write. Right? Wherever VB comes in the Kirchhoff's law loop, 1 by GM you have to write. Okay? So let's calculate the voltage gain. Yesterday we have done this. This is the popular common emitter. Or we'll do one thing. I'll give you CE amplifiers, right? CE amplifier. All the CE amplifiers are going to have 180 degrees phase shift. CE amplifier. Because whether it is CE or CB, we don't know. We have to just simply write what are the resistors in that loop. Are you getting the same method for CB and CC? Because we are just writing the ratio of voltages equal to the ratio of resistors, right? Okay. Okay, I told you the numerator current is collector and the denominator current is also collector. So in a Kirchhoff's law, V equal to V1 plus V2 plus V3. If there are 3 drops, then you need 3 resistors. If there are 2 drops in the loop, then you need 2 resistors. If there are 5 drops, right, Vin equal to VB plus IERE plus I, something like that, right? Vin equal to drop 1, drop 2, drop 3, drop 4, drop 5. Then if there are 5 drops in the loop, then 5 resistors you need, right? If there is only 1 drop, only 1 resistor. Okay. Now, this node is ground and your Vin is VB here and your V0 is across the RC. So let me write V0 by V. Please don't forget the negative sign. The ratio of voltages is the ratio of resistors. The ratio of voltages is the ratio of resistors. Now tell me, V0 comes in which loop? V0, whenever you're writing Kirchhoff's law, V0 is something to do with the resistor RC. So that resistor you have to put here, right? And in the denominator, Vin is nothing but it covers the loop with VB. I told you wherever VB is there, don't write alpha by GM, don't write R pi. If VB is there, just write 1 by GM. Wherever VB is there, just write 1 by GM. The gain of common emitter is going to be minus GM RC. The gain of common emitter is going to be minus GM into RC, right? Any problem? V0 is across RC. So only 1 resistor in the numerator. In the denominator, VB is there, 1 by GM, right? Okay. Now, the second problem, you know that if there is a voltage source and there are 1000 resistors in parallel, if there are 1000 resistors in parallel, the voltage at base terminal is going to be the same. The voltage at base terminal is going to be the same and Vin is still VB. Vin is still VB. Or you can do one thing, you can draw the Thevenin equivalent for this network. For this network, you realize that the Thevenin equivalent is only Vin, and if you short the voltage source and see, R1 and R2 are gone. So this network equivalent is the same as the first network. The same as the first network. Now, if there is a voltage division, then okay, we can do it. There is no division, it's only a parallel connection. It is only what connection? Parallel connection. Your Vin is still VB. So when you write Kirchhoff's law, won't you write Kirchhoff's law like this? Will anybody stop you writing Kirchhoff's law, or will you consider R1 and R2? There's no need for you to consider R1 and R2. Simple logic is a resistor in parallel to a voltage source has no meaning. A resistor in series to a current source has no meaning. Suppose there's a current source, you put 10 resistors in series, same current will flow. If there is a voltage source, 100 resistors in parallel, same voltage will be there. When you write Kirchhoff's law, you just jump, right? You don't consider R1 or R2. Okay, so what is V0 by V? Let me not forget the negative sign. Negative sign. So the output is across RC, so I'll put RC. The input is VB, wherever VB comes 1 by GM. So it's going to be minus GM RC. It is going to be what? Minus GM into RC. So the voltage gain of common emitter and the voltage gain, even if you have R1 and R2 are in parallel, the gain is still going to be same. Yes. Then what is R1 and R2? I told you it's a shame on R1 and R2 because they are going to affect the input resistance Rin. We've already seen Rin is R1 parallel, R2 parallel, R pi. The input resistance is gone. But luckily, in parallel connection, voltage is going to be same. So the voltage gain still remains same. Okay. Yeah. Now here I have left some space here. The reason is the voltage, now there is something called the division of voltage, and I have given you the equivalent of this network by source transformation, right? Or by Thevenin's. What is the equivalent of such a network? We have already done. This network equivalent is going to be a voltage across this R2, which is V in R2 by R1 plus R2. We have also done this with source transformation in diodes, the simple voltage divider, in series with R1 parallel with R2. In series with what? R1 parallel with R2. So now I'm going to remove this network, or you can do source transformation, V in, or you can do like this. This is V in by R1 in parallel with R1. And then you have R2. And R1 and R2 both are in parallel. Then V in by R1 multiplied by R1 parallel R2 is this voltage. So now this is equivalent to some voltage here, right? V in into R2 by R1 plus R2 in series with R1 parallel with R2. And now you have this circuit. Am I right? Now tell me, what is V naught by this? We'll call it as a Vx, right? Or VTH, your wish, right? VTH. What is V naught by VTH? V naught by VTH equal to some resistors in the numerator by some resistors in the denominator. Some resistors in the numerator by some resistors in the denominator. What resistor should I put in the numerator? V naught is across RC, so I'll put RC, right? In the denominator, this voltage has got two drops, one drop here, one drop here. If there is a VB, I will write 1 by Gm. I told you, emitter resistor should be divided by alpha, base resistor should be divided by beta. Emitter resistor should be divided by alpha, base resistor should be divided by beta. Emitter, there is no resistor, base, there is resistor. It is R1 parallel R2 by beta. R1 parallel R2 by beta. But please, what is, I don't want VTH, right? What is VTH? This guy is going to be V in into some factor. What is that factor? R2 by R1 plus R2. Now, can you send this R2 by R1 plus R2 to the numerator? Can you send this R2 by R1 plus R2 to the numerator? Then what is V naught by V? It is going to be minus RC by 1 by Gm plus R1 parallel R2 by beta into this factor R2 by R1 plus R2. R2 by R1 plus R2. So it's minus RC by 1 by Gm plus R1 parallel R2 by beta into that factor. Just send this denominator factor here to the numerator, right? So to the numerator, then you get V naught by V, right? So whenever you find a network like this, but otherwise what we've been doing in the small signal model, first we'll write small signal model, we get an extra loop. To that loop, we'll keep on writing Kirchhoff's law. One equation, two equations, substitute two in one, this, that, all drama we will do. Yes or no? So the number of equations will get difficult, right? So what happens if there are 2-3 transistors, suppose differential amplifier given to some other connection? If there are 5 loops, 5 equations will be there, 5 unknowns. It's very difficult using Kirchhoff's law. So Kirchhoff has its own limitations. What is the limitation of Kirchhoff's law? When the number of loops get big, then analysis is getting difficult. That is why we have to have some sort of a method, which of course is from Kirchhoff's law only, right? The basis is Kirchhoff's law. Intuitively, we can solve this. The ratio of voltages here is the ratio of what? Resistors. The ratio of voltages is the ratio of resistors, right? In numerator also, please don't write beta, because numerator current is IC, denominator current is IC. So this current is already IC. So there is no factor beta, right? Just write resistors, that's all. Just write the resistors. Emitter resistor divided by alpha, base resistor divided by beta. That's it. Yeah, I think this is the one which we have taken, V naught by V. Tell me what is V naught by V? some resistors in the numerator by some resistors in the denominator. So what is there in the denominator? This is ground. The voltage across this is RC. What are the resistors in the numerator? Wherever VB comes, you have to write what? 1 by GM. RB is there. So 1 by GM for VB. Emitter resistor I'll divide by alpha, and base resistor I will divide by beta. Am I right? Base resistors I'm going to divide by beta, right? Okay. This is V naught by V. And please, whenever input is given at base, output at what you call a collector, there should always be a negative sign. Oh, where is my output here? Output you can take. I told you all these amplifiers are common emitter amplifiers, right? And see here, I want V naught by V in. Where is V naught by V in? Is it in the first transistor V naught by V in, or is it in the second transistor V naught by V in? V naught is at the first transistor, V in is also at the first transistor, right? So we don't need the second transistor. So when I don't need, what do? I want to kick this transistor out. So what we have to do is we'll just put node 1 here. It's connected here, right? Node 1. Now I'm going to remove this transistor and put a resistor here. What resistor should I put from node 1 to ground? You should know what is the name of the terminal. Don't think, right? Just don't think, just know the name of the terminal. If the name of the terminal is base, it's R pi. If the name of the terminal is emitter, it's alpha by GM. If the name of the terminal is collector, it's R naught, right? So the name of the terminal is base, so it's R pi. So I'm just going to have an equivalent now. RC. I put node 1 here. From the node 1 to ground, there is going to be R pi or R pi 2. So consider transistors having the same beta value. This is V in and V naught. These two are in parallel. These two are in what? Parallel. So yeah, I need some space to write the equation. RE parallel with R pi 2. Okay, I'll find some space here. V naught by V is minus of something by something. What are the something? Resistors in the numerator by the resistors in the denominator. The resistors in the numerator is going to be RC. The resistors in the denominator is wherever VB is there, I'll write 1 by GM. Emitter resistors divide by alpha and base resistors divide by beta. So it's RE parallel with R pi 2 divided by alpha or alpha 1, right? It's the first transistor's current. The numerator current and the denominator current should be same, right? So it's minus RC by 1 by GM plus RE parallel with R pi 2 divided by alpha 1, right? This why alpha 1? Because you want very, very accurate answer. You till the second decimal or third decimal if you want. You need that factor alpha. But otherwise alpha is what? 1 for if beta is infinite, beta is very large. If examiner says beta very large, then happy alpha is 1, beta is infinite, right? If examiner says beta very large. So let me put a box for this box. This is the answer. And a box for this. So now you understand that any problem in transistors, if it is given, in a minute we are going to finish it, right? It's just an explanation, but steps. And the good thing is there are no steps in this, right? There's only answer. And you know why? This is the reason I don't want to write in the material. If you write in the material, what will happen? Some students who see that, they think that sir has given homework. Yes or no? Because no steps are there, only answer is there, right? But when you do it together, when we are doing it together, right, by discussing and step by step, then we know that we are arriving at the answer directly, right? Okay. Now, okay, voltage source should be replaced by short, but what about current sources? AC equivalent. Voltage sources are replaced by short circuit. Current sources are replaced by what circuit? Open circuit. capacitors are replaced by short circuit for AC analysis. For what analysis? AC analysis. Okay, so let me remove the current source there. Capacitors are replaced by what circuits? Short circuit for AC analysis. Now tell me, from collector to ground, what do you have from collector to ground? From collector to ground, you have R1. And these two are in parallel. And from emitter to ground, you have R2. So emitter this is the emitter resistor. R2 is emitter resistor. Why it is an emitter resistor? Because it's connected to emitter, right? It's connected to emitter. And this R1 is in parallel with RC. This is ground. This is also ground. So these two are in parallel, right? So now tell me, what is V0 by V? It is minus of something by something. So what is that you're going to do right here in the numerator? This is equivalent to RC parallel with R1. The collector resistor is RC parallel with R1. And what are the resistors in the input loop? What are the resistors? Wherever VB is there, write 1 by GM. Please don't write alpha by GM, don't write R pi. If you write R pi, it's in terms of IB. If you write alpha by GM, it's in terms of IE. Now we are writing in terms of IC. 1 by GM. All the emitter resistors should be divided by alpha. All the base resistors should be divided by beta. So it is RB by beta and R2 by alpha. It is RB by beta and R2 by alpha. Okay, now a good piece of advice, right? A student is saying that, sir, what if we do an equivalent resistance here? It'll be more practice, right? So yes, orally we can do. Tell me, what is the resistance of this circuit at the input side, Rin? Rin is also going to be R pi. What is the input resistance here? R1 parallel, R2 parallel with R pi. Am I right? So that's a very good suggestion here. What is the input resistance of this? The third one. R2 is in parallel with R pi in series with R1. So it is R2 parallel R pi in series with R1. Am I right? What about here? The resistance seen through base, right? If you go from base to emitter, there is a multiplication. Same circuit we have already done. And of course, this is the same thing. Yeah. That's a good suggestion, right? You can also calculate the resistance of this. But First time we are doing it, so I'm just training your mind, right? Voltage gain, don't think anything. Just write the resistors. Emitter resistor divided by alpha, base resistance divided by beta. Are you getting? Okay. Shall we take a break now? Shall we take a break? A small break, right? Shall we take a break? How to find for sixth problem? A resistance, same thing. RB plus RB plus 1 plus beta times of this. Yeah, after voltage gain, I'll do one thing. That's a good suggestion. I'll do one thing. Once we are done with voltage gain, I'll do one thing. I'll give you a single circuit and you have to find R in AV R naught. R in AV R naught. R in AV R naught. All the three for a single circuit. Then that will be a good practice, right? So we'll do that exercise. We'll take a break and come back. Venkat, some voice is coming. Please mute it. Venkat, some voice is there. Please mute it. Hello, Venkat. Please mute. Please mute. There is some noise. TV noise is there. Please mute, Venkat.
ఈ ఇంటి పట్ల కూడా మా అందరికీ అంతే అనుబంధం ఉందమ్మా.
బాబు వెంకట్,
ఈ ఇంట్లోనే పుట్టా, ఇక్కడే ఏరియా. ఈ ఇంటి కోసం మేము ఎన్నో కష్టాలు పడ్డాం. మా జీవితాలన్నీ
నిన్నే వెంకట్ వెంకట్ అని పిలుస్తుంది.
ఇది మరి
వెంకట్ మ్యూట్ చేయవా? Okay. Okay, can you hear me? Can you hear me? Can you hear me? Yes. Fine. So we have done the input resistance. We have calculated the voltage gain for a common emitter. Now, as long as you find a loop for Vin, irrespective of where the Vin is connected, whether it's connected at base or emitter, it doesn't matter, because all the emitter resistors are divided by alpha and all the base resistors are divided by beta, is it not? But please remember, only common emitter gives 180 degrees phase shift. Common base and common collector, they don't give 180 degrees phase shift, right? Suppose I have a common base amplifier, right? A common base amplifier. So how do we calculate the voltage gain of a common base? Here there is no negative sign. Find the voltage gain of a common base amplifier. Similarly, you can have the common collector amplifier. Whatever might be the amplifier, the procedure is same. You have to see how many drops are there in that loop. Now in common collector, because the output is taken at across RE, so you can have RE by alpha like that, and the input has two drops, the VB as well as RE. So now tell me, will the voltage gain change if I have RC there? Whether there is RC or there is no RC in the collector, your output is a function of RE and your input has two drops, VB and IERE, right? So your answer is not going to change whether there is a collector resistor or there is no collector resistor. So these are CC amplifiers. Yeah, I forgot. I told you the small signal model for NPN and the small signal model for PNP both are same. So I'll give you few PNP transistors. you can simply convert them into NPN and your answer is not going to change, right? Now, why not include PNP also? Okay, shall we solve them? So I repeat, if your input has some emitter resistors, then emitter resistors are divided by alpha, base resistors are divided by beta. So similarly, your output, now this time in common base and common collector, suppose your output is taken at collector, then it's okay RC. But if your output is taken at emitter, such resistors should be divided by alpha. Is it not? Emitter resistors, don't forget, divide by alpha, base resistance divide by beta. Because we are imagining numerator current and denominator current to be IC, right? Okay. So let's start V naught by V. Color of the pen, I want black. Why is it not changing? Yeah. V naught by V. Numerator some resistors and denominator some resistors. So what resistor should I put for output? The output is across RC here, so I'll have RC. And the input has VB. The input has VB. Wherever VB is there, write GM, 1 by GM. Please don't put negative sign. Negative sign is only for what amplifier? Negative sign is only for common emitter, right? Common emitter, right? But in common base, what is happening? The IC here has negative and Vin is minus VB. Vin is minus VB. So negative in the numerator, negative in the denominator, it is going to get cancelled. So there is no negative sign for common base and common collector. So what is the gain? Plus GMRC. This is something we have seen yesterday. The common base amplifier gain and the common emitter amplifier gain both are same, except for the fact that common emitter flips the signal by 180 degrees phase shift, common emitter, but common base, there is no phase shift, right? Okay. So what is V naught by V in here? What are the resistors in the numerator and what are the resistors in the denominator? Your V naught is across RC, so this is RC. In your V in or VS, you have VS, you have one emitter resistor and VB. You have one emitter resistor and VB. Wherever emitter resistor is there, divide by alpha, and wherever your VB is there, you have to put 1 by J. Please don't put R pi. If you put R pi, then the numerator current and denominator current should be base current. That's a different technique. Don't put alpha by GM. Then numerator current and denominator current should be emitter current, right? So I'm just putting 1 by GM because my MOSFET is going to become simpler with this idea. Emitter resistors divide by alpha, base resistors you divide by beta. Okay. Now, here we have a voltage divider, am I right? AC equivalent. You can do source transformation. And what is the equivalent at this point, at this node for this network? If you do source transformation, Vs by Rs is a current source in parallel with Rs. Re and Rs are in parallel. And finally, the amplifier is going to convert in this fashion. It is going to be some resistance here, VTH and RTH. What are the resistances here? Vs into Re by Rs plus Re. And the emitter resistor is Re parallel with Rs. Re parallel with Rs. So now tell me, what is V naught by Vt or VTH here? V naught by VTH, the resistors in the numerator and the resistors in the denominator. The resistors in the numerator is Rc. Denominator, an emitter resistor is there, your Vin is this drop plus VB drop. So it is Re parallel with Rs by alpha plus VB is there 1 by GM. But I told you, we don't want V naught by VTH, V naught by Vs into some factor. RE by RS plus RE. So if I want V naught by Vs, what should I do? I'll send this factor to the numerator. So you have V naught by Vs equal to RC by RE parallel RS by alpha plus 1 by GM into RE by RE plus RS. Now, shall I do it directly? Shall I do it directly? But this technique, I'll teach you in multi-stage. But the problem is if I do that, now student will start asking doubt, right? How did you write it, right? So I'm not going to teach right now the multi-stage, how you're going to write it directly. But I'll just write the answer here, right? Now, can I do V naught by Vs as V naught by Vx into Vx by Vs? Can I write directly? I want, because this, all this source transformation and all that we can also avoid it. But right now I'm not going to explain this. I'm telling you, right? So intuitively you can write it V naught by Vs as V naught by Vx into Vx by Vs. So V naught by Vx, this is a common base amplifier. The gain is GM into RC. And Vx by Vs, this is voltage division. The resistance seen through emitter, there is loading alpha by GM. So it's alpha by GM parallel with RE by alpha by GM parallel with RE plus RS. This is by voltage division. So if you solve this and this, both are going to be same, right? So this is this technique I'm going to teach you with multi-stage. That means even if you have 4-stage, 5-stage, the effort is the same. You give me a 5-stage amplifier, directly we will write answer. Are you getting? 5-stage, 10-stage, 20-stage, your wish, right? Just write the answer. Because I told you, the DC analysis we have done with multiple transistors. BJT is an excellent device. MOSFET is an excellent device. They provide isolation. First stage, second, when you're doing for first stage, you're least bothered about the second. When you're doing for second, you're least bothered about the third, except for a slight loading effect, right? So if you consider that, you can directly write it. So we'll do this V naught by Vs directly in multi-stage, but not right now, okay? Right now, we are doing by source transformation and, right, we are replacing this network with a single voltage in series with resistance. So like this, you can do, or like this, right? Or, so that we will do in multi-stage later. Okay, now tell me a common collector amplifier. Now we have shifted from collector to emitter. Please don't forget that emitter resistor should be divided by alpha, base resistor should be divided by beta, right? So what is V naught by V? Common collector. No negative sign, no negative sign. So what we have to do? Your V naught is across this resistor RE. So it is RE, but this is an emitter resistor, so it's RE by alpha. And in V in, this is the KVL for V in, you have two drops, VB and IER. Wherever VB is there, 1 by GM and RE by alpha. But in books, the same problem when it is given in GATE exam, this option is not there in the exam, right? This option is not there. The option was alpha RE by it is 1 plus GMRE, right? So alpha by GM, if you solve it, what do we get here? The alpha gets cancelled. It is RE by Re plus alpha by Gm. This was there in the options, right? So it's Re by Re plus alpha by Gm. So this, or you can imagine collector current. Collector current means Re by Re plus alpha by Gm. You will get, sorry, emitter current. Re by Re plus alpha by Gm, right? In the same question was asked in GATE exam, again, second time. But they wrote Re by Re plus 1 by Gm. They wrote Re by Re plus 1 by Gm. In some GATE exam, because beta is very large, they said Re by Re plus 1 by Gm. 1 by Gm. Are you getting? But the same thing in IES exam. In IES exam, they wrote GMRE by 1 plus GMRE. They wrote GMRE by 1 plus GMRE. Are you getting? GMRE by 1 plus GMRE. Are you getting? And in IES exam, there is a bit here. It said that what is the condition where common collector will give gain 1? What is the condition where common collector will give gain 1? See, when this will be 1, if your GMRE is much greater than 1, if your GMRE is much greater than 1, then your V0 by Vin is going to be approximately 1. So many bits they are created, but finally answer is same. Are you getting? Re by alpha plus 1 by Gm, which is Re by Re plus alpha by Gm, or Re by Re plus alpha is almost 1 if beta is infinite. The alpha is 0.99, IC by IE is 0.99. And in some gate problems, he said GMRE by 1 plus GMRE. So everything is same. Everything is same. These are all common collector amplifiers, right? All are same. Different ways of writing. Okay. So what is V0 by V in here? V0 by V. Tell me, what is V0 by V? Numerator, some resistors, and denominator, some resistors. So what will you write? Numerator, it is Re by alpha, because that's an emitter resistor. Denominator, you have 3 drops. Here 1 drop, here 1 drop, here 1 drop. For every drop, 1 resistor. For every drop, 1 resistor. Base resistance are divided by beta. Emitter resistors are divided by alpha. Or it is equal to Re by emitter current. If you assume emitter current, Re plus alpha by Gm plus Rb by 1 plus beta. Like that also you can write. Your wish. However, you write same thing, right? All of you, just take it lightheartedly. I'm just getting an idea, a small idea I want to share with you. The same common collector, can I do it like this, just for your say convenience? Let me write it here. I'll take a fresh page here. The 10th problem, right? The 10th problem, see here. The 10th problem. A simple idea, okay? Simple idea. Sometimes you're stuck with some ideas and suddenly you feel like sharing it. Now, please see here. Can I replace the transistor? I want to replace the transistor. Replace the transistor with the Thevenin equivalent. The Thevenin equivalent. Now you might say, oh, what is this? Thevenin equivalent is for like resistors. Now you want to replace transistor. Okay, so we'll try. I'm having a transistor here. This is my voltage V, right? My voltage V. I want to remove the resistor and I want only the transistor to be replaced by Thevenin equivalent. Now we all know that in an open circuit, you get maximum voltage, right? So the same voltage is manifested here. And we know it's an emitter follower. So in an open circuit, you have maximum voltage. I told you the Thevenin's resistance, if you see through emitter, it's alpha by Gm. It is what? Alpha by Gm. So this network is connected to Re. So I want to replace only the transistor with the Thevenin equivalent, Vin, in series with alpha by Gm. So we are finding Thevenin equivalent at this node 1. At this node 1, the Thevenin equivalent, right? From 1 here to the ground, we have Re. Wow. This is the first network we have done in the introduction. This is called the voltage division rule. It's called what rule? The voltage divider rule, right? So what does the voltage divider rule tell you? The voltage divider rule tells that your V0 by Vin is going to be R2 by R1 plus R2. It's going to be V0 by Vin. Like this also we can do. It is Re by Re plus alpha by Gm. Okay, right? So some idea, okay? Don't take it very seriously, take it lightheartedly, right? Whenever you find a transistor at the emitter, you can have a good Thevenin equivalent for it, right? So you just remove the whole transistor and then you can solve the simple voltage divider. So this way you can avoid the small signal analysis, right? Okay. Did we get the same answer here? Yeah. Right? Re by Re plus alpha by Gm, we got that. Fine. So the transistor is replaced by what equivalent? Thevenin, right? So solving common collector, CC amplifier. Okay. And yeah, a student was saying, sir, can't you do the resistances also simultaneously? Yeah, we can do it, but it's okay. We are just finding the voltage gain. If you want to do the output resistance of this amplifier, okay, R0. What is the output resistance of this amplifier in Thevenin's? In Thevenin, whenever you want to find the output resistance, the voltage source should be short. Am I right? So your R0 is also going to be alpha by Gm in parallel with Re. In parallel with Re, if you short the voltage source here, right? Short the voltage source here. Okay, doesn't matter. Our aim is only voltage gain, so just calculate the voltage gain. Okay, so many ways of doing, but finally the answer should be same, right? Finally the answer, however you do, your answer should be same. Okay, this is where we stopped. We have to do this. Now, all of you, just stop writing and observe. Just stop writing and observe, right? What did I tell you for PNP transistors? I told you that after writing AC equivalent, draw the NPN and make the connections, right? So what are the steps now? Step 1, draw AC equivalent first, AC equivalent, and then step 2, replace or draw NPN transistor and reconnect the resistors. And reconnect the resistors, right? So first we have to draw the AC equivalent. For AC equivalent, what should I do to voltage sources? The voltage sources are short at ground, right? Am I right? Why am I not getting this black pen? Yeah. Now, let us reconnect, draw the AC equivalent. Now draw the NPN transistor. See here, how do you draw the NPN transistor? The NPN transistor is drawn like this. This is an NPN transistor. Am I right, sir? And what are the terminals here? This is base This is emitter and this is collector, right? Any problem? Base, emitter, collector. And now we have to reconnect them. Here this is collector, emitter and base. Collector, emitter and base. So we go step by step. The emitter is connected to ground. So connected to ground. So any problem, emitter to ground? No problem. From the collector to the ground, we have RC. RC. Where you take the output. And input is given at base. Oh, this is a basic common emitter amplifier, right? This is a common emitter amplifier. And what is the gain of common emitter? Minus GM into RC. Or you can do like this, V0 by Vin. Please, common emitter always give you a negative sign. It always give you a negative sign. It's RC by 1 by GM for the input. Wherever VB is there, 1 by GM, it is minus GM RC. Common emitter is going to give you a gain of minus GM into RC, right? So this is the PNP version of a common emitter amplifier, a CE amplifier, right? Input is given at base, output is taken at collector. Input is given at base, output is taken at collector. So this is a common emitter amplifier. This is a CE amplifier, CE amplifier. This is a CE amplifier, right? Okay. Now, why don't you try for the 13th one also? The 13th one. First, draw what equivalent? AC equivalent. AC equivalent. Now you convert the PNP transistor to an NPN. So you have to draw the BJT like this. Draw the BJT like this and reconnect them. Collector is connected to ground. Collector is connected to ground. Emitter to ground, there is RE. Base terminal is at V. So this is our common collector amplifier. So what is V0 by V in common collector? It's RE by alpha plus 1 by GM, or it is RE plus alpha by GM. RE by RE plus alpha by GM. Okay. Now tell me the same thing. Draw the AC equivalent. For AC equivalent, the DC sources should be grounded. The DC sources should be grounded. The DC sources should be grounded. Now, reconnect the resistors, right? So draw the BJT and reconnect them. From emitter to ground, you have RE. Collector to ground, there is RC. Base terminal is at V. Base terminal is at V, right? So this is also a common, this is also what amplifier? A common emitter because output is taken at collector, input at base. So it is minus RC by only RC, and at the input loop, what are the resistors? You have RE by alpha plus 1 by GM. RE by alpha plus 1 by GM, right? Okay, so let's draw the AC equivalent. Capacitors are replaced with short circuit. So this is equivalent to oh, I don't have place now to do it. And in the next page, you have common collector. What should I do? No place to solve, no place. Yeah, I'll do by this trick, right? I think V naught by Vs. For that, I think this space is enough. V naught by Vs is V naught by Vx. I want you to replace the voltage divider with a single resistor in series with a voltage source by source transformation. So you can do by source transform. I'll write it directly. V naught by Vx is minus GMRC, that's a common emitter. And Vx by Vs, by voltage division, there's a loading of RB there. RB parallel R pi by RB parallel R pi plus RS. Okay. So you solve it by the method which we have done till now and just compare your answer, right? The answer is not going to change. Okay, so somehow it fits in this place. Because here we've done the common collector in the next page, replacing the transistor by the Thevenin equivalent. Just a fancy way of doing it. Thevenin equivalent, right? So I'm going to shift the frames. You If you want, you can take the screenshot. Okay. 5 seconds, 5 seconds. Yeah. Anybody who has missed taking screenshot can take. Okay. Now take a deep breath. I'm going to give a single circuit, calculate voltage gain, input resistance and output resistance. And as I told you, because early effect is not introduced, output resistance is collector resistance. Remember, output resistance is simply collector resistance. Input resistance and voltage gain we have already seen. Now, I'll give you a single circuit, calculate input resistance, output resistance and the gain. Oh, yes. Calculate AV, Rin, R0. Calculate AV, Rin and R0. Calculate AV, Rin and R0. And remember, output resistance is simply the resistance at collector terminal, right? Collector. Calculate AV, Rin and R0. Or we'll take the, after all this CB, CE, CC, I told you we might go to amplifiers like this, right? So once we finish common source, common gate and common drain, we have to go for structures like this, right? The differential structures for this or. So even without knowing what is the benefit of this structure and all that, we are simply calculating Rin, R0 and AV, right? Rin, R0 and AV. And if I give it in PNP, please convert it into NPN and do it, right? Okay. Yeah. Now this upper transistor, this is a diode. We can replace this guy by 1 by Gm parallel with R pi. Am I right? 1 by Gm parallel with R pi. So we can have something like this. Am I right? Now, what do you think we have to find first? What do you think we have to find first? If you want to find voltage gain, then simple logic is emitter resistor should be divided by beta. Alpha, base resistance should be divided by beta, and you have to write. But if you want to find the input and output resistance, then you have to know the name of the terminal. The name of the terminal. What is the name of the terminal? Base terminal, the resistance is R pi. Emitter terminal, resistance is alpha by Gm. Base terminal, the resistance is R pi. Emitter terminal, it is alpha by Gm. Collector terminal, if there is no early effect, it is infinite ohms. If there is early effect, we will have R naught. We will have what? R naught, right? And if you go from base to emitter, if there is a resistor at emitter, then you have to multiply by 1 plus beta times. If you go from emitter to base and there is a resistance at base terminal, that resistance should be divided by 1 plus beta, right? Okay. Suppose you want to find the input resistance Rin. So what is Rin? What is the name of this terminal? The name of that terminal where the input is connected is called base terminal. At base terminal, the resistance is R pi. And from here to ground, from this node to ground, you have to reach R pi plus 1 plus beta times of Rin. This is Rin. And what is the voltage gain? This is a common emitter amplifier. In a common emitter, numerator some resistors, denominator some resistors, right? So the numerator says that V naught is across RC plus 1 by Gm parallel with R pi. Why plus? Because they are in series. They are in series. Resistors in series, you can add. And in the V in this loop, it has two drops, VB and then IER when you write Kirchhoff's law. So wherever VB is there, write 1 by Gm and RE should be divided by alpha for voltage gain. And what is the output resistance? The output resistance is the collector resistance. The collector resistance is generally RC, but now RC has come in series with this. So it is RC plus 1 by Gm parallel with R pi. Is 1 by Gm parallel with R pi, right? So this is how, and just imagine if at all you want to do by small signal. First, two loops that with two transistors, then a short, then a resistor in the middle, and then a R pi and beta IV or GMVB, and then a resistor, and then you have to apply. It takes time, is it not? It takes time. Instead, if you do intuitively, so analog is all about intuition, right? Intuitive analysis, then definitely it is going to save time. It is definitely going to save time, right? Okay. Now what about this one? The same thing here. RC. And who is this guy? 1 by GM parallel with R pi. So tell me, what is Rin? Rin is going to be, you're seeing through the base terminal, R pi plus 1 plus beta times of 1 by GM parallel with R pi. Suppose it is Q2, 1 by GM2 parallel with R pi 2. This is R pi 1, right? What is the voltage gain AV? It is minus of something by something. So what will you write in the numerator? RC. Denominator, there are two drops here. V in this drop plus this drop. 1 by GM plus 1 by GM2 parallel with R pi 2 divided by alpha or alpha 1, right? And output resistance is going to be collector resistance. Collector resistance is output resistance because we don't know this is going to be infinite. Infinite parallel with RC. When you see from here, infinite parallel with RC is going to be RC, right? Always remember, output resistance is simply collector resistance. Output resistance is simply collector resistance. Right? Output resistance is simply collector resistance. Okay. Now what about this circuit? Now where is V0 and Vin? Where is V0 and Vin? Are they connected to Q1 transistor or Q2 transistor? Are they connected to Q1 or Q2? They are connected to Q1. If they are connected to Q1, I want to just remove this whole transistor here. I want to cut that. So what is the resistance seen through emitter? What is the resistance seen through emitter? The resistance seen through emitter from node 1 to ground is alpha by GM. Alpha by GM. Of course, this circuit, please, we are going to do again in differential amplifier, but without condition, symmetry, nothing, right? We don't know anything about it, but we are simply solving a differential amplifier, even without knowing a differential amplifier, right? So what is the input resistance Rin? Rin is going to be R pi plus 1 plus beta times of alpha by GM. It is R pi 1 plus R pi 2. We have already proved this, right? And what is voltage gain, AV? It is minus of something by something. It is RC by alpha by GM by alpha plus 1 by GM. Alpha alpha cancel. Minus RC by 1 by GM plus 1 by GM. It is going to be minus GM RC by 2. So I'm going to directly prove this in a differential amplifier, and I'm going to tell you that Left side, if you take, it's minus GMRC by 2. Right side, if you take, it's going to be plus GMRC by 2. We'll do this in differential amplifier. But without knowing anything, we have solved this by the resistance reflection rule, right? And what is the output resistance R0? It is the collector resistance. Collector resistance, and the collector resistance is going to be RC. RC, right? So because symmetry is involved in a differential amplifier, when we see take up differential amplifier, you realize that the total Rin is R pi 1 plus R pi 2. The voltage gain is going to be minus half of the common emitter amplifier, right? Minus GMRC by 2. And the collector resistor is simply RC. This is R0. R0 is RC. This is Rin here, right? Now, one more piece of advice here. Some students have a doubt that, sir, when you're seeing through base terminal, why you are not considering collector RC and all that? You're just saying R pi. The reason is a transistor equivalent, if I'm not exaggerating this, can be drawn like this, right? This is a transistor equivalent. Between base and emitter, what is there? Between base and emitter, what will you write? R pi. Between collector and emitter, there is beta IB or GMVB. So the same transistor, can I draw it here, right? I want to draw it here, here. So this is my collector. It is GMVB, all right? It looks exaggerating, but this is a good way of drawing, right? This is also a small signal model. So next time you get a doubt, right? When I'm looking at base, what happens at collector? Nothing happens because you can't see that collector. If you're seeing this collector, it's better you draw still far, right? You draw it so far that next time you don't see it, right? Whenever you're looking at base, what happens at collector is least bother, right? But emitter is connected both to base as well as collector. But base terminal, if you're doing R pi plus 1 plus beta times Vari, don't worry about the collector resistors because there's no connection, right? Okay. See, tomorrow also we will have only 2 sessions, right? We will have 2 sessions. Probably we'll start from what time you want. We'll start from 2 and wind up at 6:30. 2 to 4, one slot, have a break. And then 4:20 to 6:30 like that, right? So only 2 sessions we will have. I mean, till 8:30 or 9, it's getting difficult, right? So I'm literally getting back pain, right? Sit for 3 sessions. I'm not used to this. So is it okay for you, right? Yeah, only 2 sessions, please, tomorrow, right? Okay, so what is the last thing that we have missed? In a BJT, there are 3 terminals, base, emitter, and collector, but we talked only about 2. And the third terminal, we didn't talk about it because most of the gate problems are not with early effect, right? Now we are going to include early effect. One simple R naught we are going to include, that's all. And what is a multiplication factor if I go from collector to emitter? Please see here, your R naught, where is your R naught here? Where is your R naught in this? Your R naught is somewhere here, somewhere here. So there is no multiplication factor from collector to base because base is not there. There's only one multiplication factor between collector to emitter. If you connect a resistor from collector to emitter, what is the multiplication factor? We are going to do this. I'm going to prove this. This is my rule. How many rules I've given? 1, 2, 3, 4, 5. This is my last rule, rule 6, right? My rule 6 says that if you have a BJT or a MOSFET, both are same. If you have a BJT or a MOSFET, and if there is a resistor R, then you have to consider that there is something called R naught here. There is something called R naught, right? There is something called R naught or BJT. So what is the output resistance here? There is something called R naught you have to consider. So I'm going to prove that the output resistance R naught is going to be R naught plus some multiplication factor into R. Some multiplication factor into R. That multiplication factor is 1 plus GMR naught. That multiplication factor is 1 plus GMR naught. I will prove and I'll get back to this slide, right? We'll get back to this slide and I'll prove it, right? So rule 5, what is the multiplication factor? MOSFET or BJT, both are same. But only difference is in a MOSFET, there is no VGS or VB. This is V pi. This is an open circuit. GM VGS or VB, V pi in parallel with R naught. So I'll give you this small signal model later, but I'm just telling you, if I put a resistor here between plus and minus, if I put a resistor, it becomes a BJT. If I don't put a resistor, it is going to become MOSFET, right? It is going to become MOSFET. So this is gate, source, and drain. So that way MOSFET is much, much simpler. Or if you don't like this model for MOSFET, some students are asking, sir, can we have a Thevenin model also? Yes, you can have a Thevenin also. So if you want a Thevenin model of a MOSFET, then how you can write a MOSFET or a BJT? This is GM pi. What is the current in opposite? Minus. So minus plus GMR naught into V pi. GMR naught into V pi in series with R naught. You can take like this. Because if the current flows in this direction, it is going to be minus GM pi into R naught. Or you can take plus minus, and put a negative sign here. Put a negative sign. Minus GM pi into R naught into V pi. This is by source transformation. This is by what transformation? Source transformation. Or you can interchange the polarity. You can interchange the polarity and write it like this. Minus plus, then the negative sign vanishes. GMR naught V pi in series with R naught. So you can do like this. So this is a MOSFET small signal model. This is what model? Norton. This is Norton. This is the Thevenin. The Thevenin to Norton is done by source transformation. What is source transformation? let me write it here, source transformation. First class I've given you, but if you have forgotten, what is source transformation? If I have a voltage source in series with resistance, then I can equate this to a current source in parallel with the same resistance. Am I right? So if you have a current source, then I in parallel with R is nothing but V equal to IR. V equal to what? IR. This is the current here. V equal to IR in series with R. So now you have I, but this I is in the opposite direction to this current. So if you take here, you'll always have a negative sign. See here, plus minus, there's an extra negative sign because of the arrow here. Here the arrow is up. Am I right? So this is called the source transformation. This is called what? The source transformation. Okay. Okay, so this is all about the MOSFET. We have not done this. Now, why there is a multiplication factor 1 plus GMR naught? 1 plus GMR naught. Tell me, how do you calculate output resistance? You have to connect a voltage source V and find current I. Then output resistance by Ohm's law is V by I. Output resistance by Ohm's law is going to be V by I, right? Now, please, only once we are doing this proof, and after that, we will remember this factor, 1 plus GMR naught, and then we will ask, give me 5 MOSFET, 10 MOSFET, 5 transistor, 10 transistor. I'm going to keep on multiplying 1 plus GMR naught, 1 plus GMR naught, 1 plus GMR naught. I'm going to get it. So that way, even early effect becomes simple, right? So this is V pi. Here you have GMR naught V pi in series with R naught. And from source terminal, this is source, gate and drain. Gate, source and drain. So from source terminal to ground, there is R. There is R. And here, and from source terminal to ground, there is R. And here, why this has come here? Now, because this is an open circuit, the same current I will flow here. The same current I. Now, give me a KVL. KVL, this is ground. This is also ground here. Give me a KVL. V pi plus IR equal to 0. So, your V pi is minus IR. Your V pi is minus IR, right? Give me one more KVL in this loop. In this loop. Tell me. Minus V plus I into R naught minus GMR naught V pi plus IR equal to 0. So in the place of minus V pi, what will I write? I into R naught plus GMR naught into I, R into I plus IR, right? This is minus V plus this value equal to 0. From here, what is V by I? V by I is R naught plus 1 plus GMR naught into R. So it is R naught plus K times of R. It is R naught plus some value K times of R. That's a multiplication factor. And that KR is going to be how much? 1 plus GMR naught. Now you might ask me, sir, why did you derive MOSFET? We are doing BJT, no? Why did you derive MOSFET? See, I was a little lazy here because for BJT, you tell me how the rule changes for BJT. If I am seeing from here, please see here, I am seeing from here, right? Draw it somewhere at the corner here and imagine there is a resistor R here. There's a resistor. Now just tell me how this R pi and R will look like when you are seeing from the drain or from the collector, somewhere far, just draw somewhere far. Okay, let me draw it here. If I'm having R pi here, this is ground, and this end is also ground. Here, this is R, and I'm seeing somewhere from here, right? From here. When I see from here, how are these two resistors? I'm saying, how are these two resistors? These two are in parallel. These two are in parallel. So I don't have to waste time deriving it. What will I do now? I'll go back here and say that this, there is no R pi here, but here there is an R pi. So if you see from here, your R naught is going to be R naught plus 1 plus GM R naught into R parallel with R pi. So please, I repeat, this extra R pi is going to come if it is the BJT. But there is no R pi, your R pi is infinite. Infinite in parallel with R is going to be R, right? So just to avoid, see who wants to derive the same thing 2 times, right? So I just derived for MOSFET here. And then I'm motivating you saying that if you're seeing from a very far distance here, how this R pi and R are, this is a point, right? Suppose this is a point X. So we'll take X here, this is ground. From X to ground, there is R. From X to ground, there is R pi, right? So if somebody's seeing from a corner, from somewhere at this point, then these two resistors will look to be in parallel, right? So I repeat, very, very important. Let me put a star mark here, star mark. This is rule 6, rule 6. So can you remember rule 6? If it is a MOSFET, it is R naught plus 1 plus GM R naught into R. If it is a BJT, it's going to be R naught plus 1 plus GM R naught into R parallel with R pi. R parallel with R pi. Remember, it's R parallel with R pi. It's R parallel with R pi. R parallel with R pi. It's R parallel with R pi, right? So if you remember this 1 plus GMR naught factor, we can solve so many problems just by multiplying that factor, 1 plus GMR naught, 1 plus GMR naught, 1 plus GMR naught, 1 plus GMR naught. Okay, so we'll stop here. So tomorrow we are going to see the what you call 1 plus GMR naught, the multiplication factor if you go from collector to emitter or from drain to source, right? Only one is left, the early effect is left, 1 plus GMR naught. So tomorrow we will see this, okay? So any questions you have, you can ask me now. Okay. Venkat, unmute. Unmute Venkat.
Hello.
Yes.
Good evening, sir.
Evening.
Sir, I have doubt in yesterday's lecture. Sir, we did that MOSFET questions, and in some questions we were directly finding ID. In some questions we were actually finding out in which region that the MOSFET was present. So how to have that intuition, sir?
Yeah, I mean, after calculating, first you can directly assume the MOSFET to be in saturation. Once you are done with calculation of currents, then you have to check whether VDS is greater than VGS minus VT. If it is false, then you have to go back to triode again.
Yes, sir, that is one method, but I'm asking how to have that intuition that if this circuit is like that, then we should check whether it's in saturation
I
or
mean,
not.
if the gate and drain are shorted, then such problems, there is no need for us. Directly we know that VDS equal to VGS. So that means VDS will always be greater than VGS minus VT. So such problems, the gate problems we have done, you can always assume it to be in what region?
Saturation.
Desaturation and do it. Yeah.
Okay. Otherwise, we should check if they are.
Otherwise, just calculate. After calculating, just see whether your VDS is greater or not. It's just a matter of seeing whether your drain is at a higher potential than source.
Okay. And also, sir, when we were doing that analysis of biasing with emitter resistor,
Yeah.
and RE characteristics, sorry, that thermostability point.
Okay.
And we said that RE thermally stabilizes the circuit, and you said something about that we don't have to use aluminum that much to.
Yeah. I mean, generally we were using some power amplifiers. I don't remember, CA3055 or something. The size of heat sinks were big. So then it was advised that why not put small 1 ohm resistors? Because today we have seen that emitter resistors will reduce gain. So we don't want to put large value of resistors so that the gain will reduce. But at the same time, we wanted thermal stability. So we had to put small 1 ohm resistors such that the gain will not reduce. And at the same time, we get the size of heat sinks we can reduce. See, it's very simple.
But my question was that resistor is actually a heat element itself. So how is it helping reduce the temperature?
No. There's something called the runaway problem in the BJT. If your temperature increases, and that temperature will in turn increase your IC, the IC will in turn increase the temperature. So see, I don't know how to give this analogy. There are two ways of stopping the fevers. When my kid gets fever, there's two ways. My wife always says that don't go for paracetamol. Take a wet cloth and just put it. Okay. So what does this do? The rate at which the heat is generated, more faster, it has to dissipate. It has to remove the heat. The heat sink is something like that. See, it's not that the transistor will get burnt. If you have a good heat sink, then the rate at which the heat is generated, more quicker it is going to release it. Or you can use a fan. If you're rich, you can use AC also. But we generally use the heat sink because we just want to remove the heat. That is one way. The other way is I told you, you can take a paracetamol and then stop it. Because the doctor was telling me that the paracetamol can create some sort of negative feedback where the increase will try to decrease. So this emitter resistor is also something like that. You connect an emitter resistor, any increase will try to decrease there. So emitter resistor is a good solution, but if you don't have an emitter resistor in a power amplifier, the only way you can remove that heat is by providing a heat sink.
Okay.
Are you getting?
Yes, I got it. Thank you. Thank you so much.
Hello, sir.
Yes.
Sir, 12F, sir.
Yes.
12F.
12F, yeah.
Sir, here can you explain in Q2, 7th problem, Q2, how we got that 1/GM parallel RP?
We have already taken, no? In the rule 5. Where is it? Yeah, this is a rule 5 here. Can you see?
Yes, sir.
Here, both base and collector terminals are shorted. And I'm looking at base terminal. Then I got this RPi GMVB. If the voltage across the current source is VB and the current is GMVB, what is resistance? Resistance is voltage by current. If voltage is VB, current is GMVB, then the resistance is going to be 1 by GM. So this current source itself will give you 1 by GM. 1 by GM is in parallel with RE. That's all. That is the resistance. Or you can apply Kirchhoff's law. Entering current equal to leaving current. KCL. Are you getting?
Yes, sir. Got it.
Yeah. Now the
Sir,
question is, if you see through base terminal and inject a current, how this current is going to get divided? As IB as well as IC. Can you see?
Yes, sir.
If you see through emitter terminal, it is already IE. What is IE? IB plus IC. So whether you see through base or emitter or collector, it is 1 by GM parallel RPi only. That means you can treat this as a load. Whenever you find that such combination of a transistor, you can just remove it and replace it by 1 by GM parallel with RPi. Are you getting?
Sir, yes, sir. Got it.
Yeah.
32F, sir.
Yeah.
Sir, I think not this 31 or 33 or 30.
This one?
Yes, sir. In between two resistors, we are connected on grounds.
This is all I have.
Sir, actually, my doubt is between two resistors, you are connected on ground, no, sir.
Between two resistors, I've connected ground. Where did I connect? Which problem is that? This one? This one? This one? This one, no?
Oh, this one, sir.
Yeah.
Sir, actually, in diodes, you said in one turning problem, you said between two resistors, if you connect ground, one resistor will become negative of the other, no, sir.
You phase splitting, huh? Yeah, you are right. Yes. That means if you take the output at emitter here, see here, very good. Excellent point you have made. See here, suppose somebody takes the voltage at emitter and somebody is taking at collector. Collector voltage will be 180 degrees out of phase as emitter. That is why we get a negative sign. Are you getting?
Yes, sir.
Why common emitter gives negative sign? Because you are taking here. But if you take it here, then you are going to get positive sign because the RE resistor and RC, this is RC, no? R1 is RC. This is RE. R1 is nothing but RC, no? R1 parallel RC. So R1 and RC, that means RC and RE, they are acting as phase splitters. Excellent. You are correct. That is why common collector will not give any phase shift. Common
Okay,
emitter will give phase shift because you are taking at collector. Okay. Now what is that to do now? You're right. Absolutely right.
Sir,
Yeah.
good evening, sir. Could you please open 27 page?
27. Good evening. Good evening. 27. Yeah. Tell me.
Sir, here in this expression, I didn't get how you wrote RPi and those things.
Where are we? No, I told you. This is why I don't want to write this. I told you I'll explain this in multi-stage, right?
Yes, sir.
Are you getting?
Yes, sir.
You want me to explain now? See, because there we are going to do cascode, common emitter with common base, common emitter with common collector with common base, this combination, no? Then directly we will write this answer, even if there are 3-4 stages cascaded. Then we will have to consider this loading, that extra RPi we have to consider, because that RPi is going to come in.
Okay, sir. Yes, sir. Hello, sir. Hello, sir. Hello, sir.
Wait for 5 minutes, yeah. వచ్చిందా? ఓకే అన్న.
Hello, sir.
Yes.
Hello, good evening, sir.
Yeah, good evening.
Sir, I had a doubt in actually 30F. Actually, many questions, but one of among them is 30F. Sir, in some questions, we used one of transistor as load and we replaced it with resistor. And doing so, we took 1 by GM to parallel R by 2 like that. So in solving such questions, you mentioned that beta of both the transistors are having beta is same for both transistors. Is it of any significance?
No. They're not needed. But what I'm saying is once that transistor is replaced by a resistor,
Yes, sir.
now the Kirchhoff's law is only with the Q1 transistor. No, the first one. It's
Yes, sir.
beta only, you have to divide it. Alpha, beta. See, the moment you remove a transistor and replace it with resistor, that transistor beta you don't have to worry, I'm saying.
Okay, that's what I'm on, because in 30F,
That transistor
30F
beta you don't have to worry. Generally in exam what they'll do, beta 1, beta 2, they will not give beta, that's all.
yes, sir. Sir, in 30F, for example,
30.
Yes, sir, 30.
Yeah.
Here, if the lower transistor Q2, it is connected in the base side, and if we have to replace it with resistor, then we have to divide it by beta na, sir. So
Absolutely.
then it will
Absolutely.
be beta of Q1. I mean, if it is given like beta 1, beta 2, otherwise if it's single beta. Okay.
Yeah.
Okay, sir. Thank you very much.
Good,
Thank you,
good.
Hello, sir.
Yes.
Sir, actually you have explained the 3 capacitor significance, sir. Input capacitor, bypass. Sir,
They
can
are
you please
charging.
explain?
They are simply charging, that's all. Every capacitor is just charging so that they want to maintain transistor in active region. If capacitor is not there, for example, let me explain you like this. Yeah. See, the first capacitor that we connected is similar to this network, no?
Yes, sir.
Yes or no?
Yes, sir.
Now, this is given to BJT. If suppose capacitor is not there, directly if you supply the voltage here, BJT might go to off, cut off. So that is the reason, let me calculate this VB first. So for calculating VB, let us apply superposition theorem. What is superposition theorem? Doing DC analysis separately and AC analysis separately. In DC analysis, capacitor is replaced by open circuit. And Vin is short. Only one source you have to take. Then what is the voltage VB? VB is going to be, if this is VCC, it is VB is VCC R2 by R1 plus R2. But the capacitor, now it is going to act like short circuit for AC analysis. Now this is voltage is going to be V. So the total voltage VB is going to be VCC R2 by R1 plus R2 plus V. This VCC R2 by R1 plus R2, I told you 4 volt plus V. Do you remember? Yes or no? That
Yes,
4
sir.
is stored here. So instead of doing all this, I am simply saying that capacitor will store charge. This voltage is going to be VCC R2 by R1 plus R2.
Okay, sir.
Capacitor will store charge. That's all. Are you getting?
Yes, sir. Yes, sir.
Yeah.
Sir, you mentioned like if you connect at collector side, it will like bypass. If you connect at emitter side, it will bypass.
No, whatever capacitor that is connected across a resistor, that resistor is going to get bypassed. In common emitter, RE is getting bypassed. In common collector, RC is getting bypassed.
Okay, sir.
Are you getting? If
Yes,
a
sir.
capacitor is connected across a resistor. For AC analysis, that capacitor will act like short, no? So naturally that resistor will get bypassed. In common emitter, RE will get bypassed. In common collector, RC will get bypassed.
Okay, sir. Got it. Sir.
Okay, good.
Sir, 29, sir.
Yeah.
Sir, here 29. No, sir. 28, I think, sir.
Yeah. This one.
Sir, in one problem, you
This
have
one,
applied directly in shortcut. Yes, sir. Here, when we apply Thevenin equivalent, here I am not getting R pi, sir, in result.
You are not getting
R pi.
if you do by normal method.
Yes, sir.
Yes. This answer and that answer both are same.
No, sir. Like R pi term, you will not get, right, sir, if you do normal method.
You will not get, but you will get some term like 1 by GM like that, no?
Yes, sir. Yes, sir.
That beta by GM is nothing but R pi, no?
Okay.
R pi is nothing but beta by GM.
Yes, sir.
R pi is beta by GM. If you solve, you will get same thing.
Yes, sir.
Yeah.
30th, sir. Sir, in actually in gate questions, if they ask R naught value, then we need to consider early effect, sir.
Yes. That we will do tomorrow, no? Because we have this 1 plus GM R naught factor. Now you can play with early effect also.
Yes, sir. Like every time we need to consider, sir.
No. Examiner will give. If R naught is infinite, why will we consider? If the examiner says no early effect, don't consider R naught. R naught is infinite.
Okay, sir. Sir, in the 30th R naught, how you took, sir? I am not getting.
TF. This one, huh?
Yes, sir.
Collector resistor is output resistance, that's all. There is no R naught. Only collector resistor is output resistance. Tomorrow what we are going to do, this resistance and that RC are going to come in parallel, no? So here we are going to do R naught plus 1 plus GMR. Tomorrow we will do that.
No, sir. One value you took infinite, sir.
Yes, my dear. This transistor, if it is no R naught, it is infinite.
Okay.
Let me write it like this. I am having RC here and transistor, R transistor here. And I want to find resistance. It is
Yes,
RC parallel with R transistor. Okay. This R
Okay, sir.
transistor is infinite if there is no early effect. If there is early
Yes.
effect, it is R naught. So what is infinite parallel with RC?
RC.
Are you getting?
Yes. Okay, sir. Thank you, sir.
Yep.
Hello, sir. Hello, sir.
Yes.
14F.
14F. Yeah.
Sir, in this you R parallel with alpha by G. Fourth row, how you apply, sir?
Yeah, that's what. You want to remove this transistor, no?
Yes, sir.
We want to remove this transistor. So we had to cut it at that point and we applied it. This is I'm having one transistor like this. Okay.
Yes, sir.
And this is connected to another transistor here. And you have to find here. What should I do? I want to cut it here. This is node 1. Okay. From node 1 to ground, I want to connect. So this is what is the name of this terminal. The name of this terminal is emitter. So the emitter resistor here is going to be how much? Alpha by GM. So you just cut it completely and put alpha by GM here. And what is the resistance here? This is going to be alpha by GM plus whatever the resistance is there, that is going to get divided by 1 plus beta, no?
Fourth row, what is, sir? Base base resistor, fourth row, sir.
What?
How will we identify the fourth row, sir?
No. Identify means you should know what is the name of the terminal. That's all. Identification means names you should know for this. When a connection is given, you should know that this is emitter. You should know this is base. You should know this is collector. That name, if you know, means that is enough. So when this is connected here, you should know what is the name of this terminal. Can you see? There is one arrow here. That
Yes,
means
sir.
this is what terminal?
Emitter.
So that name, if you know, then you can remove. No? You can just remove and write alpha by GM. Suppose the same thing is connected like this. Is connected like this. Now what you will do? Now we want to cut it here, but you should know the name of this terminal. No? What is the name of this terminal?
Base.
Base. So if you know it is base, then you'll remove it and put R pi here and remove this.
Okay, sir. Yes.
Are you getting?
Yes, sir.
Yeah, you should know what this base means R pi, emitter means alpha by GM. The name of the terminal, if you know, you can remove that and put that resistor.
Okay, sir. Sir, in a common emitter, for common emitter only minus common base common filter for positive how, sir? In follow.
Yesterday we have done no problem. Only in common emitter, the collector, the output is coming from the ground node, no?
Yes.
Here, this is RC. You're taking here, IC. V0 is minus ICRC. Vin is VB. Only here there will be 180 degrees phase shift. But if you are doing common base and give, your Vin is minus VB. Vin is minus VB. V0 is minus ICRC. Minus will get cancelled, no? Common base will not have phase shift.
Okay, sir.
Okay.
Thank you.
Sir, 25F.
$25F. Yeah.
Sir, here V0 is equal to RE by alpha, but I see V0 RE only.
You want to see V0 RE? Yeah, like that also we can write.
But sir, why we took RE by alpha?
Because numerator current is collector current, denominator is collector. You and I know that there is no collector, there is emitter, no? We are
Yes,
just
sir.
doing cheating here.
Okay.
We wrote everything in terms of collector, but actual current you and I know that there is an emitter current here, there is a base current here, there is a VB here. Yes or no?
Yes. Okay, sir. Sir, now I got it. Sir,
Now you got
basically,
it. Okay, if you want to write in terms of emitter current, because you don't like that alpha in the numerator,
No,
you
no,
do
sir,
one thing.
I have no problem. Sir,
You don't have a
sorry.
problem? Okay. No, if you have a problem, then it is emitter current in the numerator and the resistance seen through emitter is alpha by GM plus RB divided by 1 plus beta plus RE. Like this also you can write.
Yes, sir.
Yeah, this
Okay.
is the resistance seen through emitter, no? What is resistance seen through emitter? Alpha by GM
Yes, sir.
plus RB divided by 1 plus beta plus RE.
RE. Yes, sir.
Like this also you can write.
Okay, sir.
But now we are doing cheating here. We know there is emitter current, but we are writing in terms of collector current.
Because sir, emitter current and collector current are same.
They are same means one
Yes.
alpha will be there, no?
Yes, sir.
Alpha
Only
will
alpha
be
will
there.
be there.
Just
alpha. And sir, in rule number 3, it's alpha by GM, or we can say R pi by beta plus 1 because
very good, very good. Both are same.
sir,
Alpha, you
sir,
can say
because-
R pi divided by 1 plus beta. Yes.
yes, sir, because in the base the resistance is R pi, and when we are seeing in emitter
The current is 1 plus beta times.
the current is 1 plus beta times, so
Excellent,
the resistance
excellent.
will.
Yeah, will get divided. Excellent.
Sir, I have a silly doubt also.
Yeah.
Sir, I don't know why I am thinking about when we are seeing AV, when we are calculating AV, why are we not transforming the transistor into resistors?
That's exactly what I have done. Thevenin equivalent in that common collector.
Sir,
I replace the
voltage
whole
gain.
transistor with resistor, no?
Sir, in voltage gain, sir, can you show me?
Yeah, this one, see here, I'll show you. Where did I do it? Yeah, this one. Can you see?
Yes, sir.
The whole transistor I replaced with a resistor in series with a voltage source.
Yes, sir.
Yeah, this is also one technique. So many
Okay.
are there.
Okay, sir. When we can do it with this technique also.
Yeah. I've proved the answer also, no? Same.
Yes, sir. Yes, sir. Sir, it was. I thought it was difficult, so I let it go.
Okay. Very good, very good.
Sir, also, sir, if I have any doubt from the previous class, because I joined in late, I joined from the 11th class. And
You have my phone number, right? You can
yes,
post.
sir. Okay, sir. If I have any doubt, I will text
Post.
you.
Yeah.
Thank you, sir.
Okay.
Hello.
Yes.
Yeah, good evening, sir.
Yeah, tell me.
Sir, page number 23, sir.
23.
Yeah, actually, sir, my network gone, so I didn't even.
Yeah.
Yeah, can you please explain the second one, sir?
The second one. Eighth one, you mean?
Yes, sir.
Yeah. See, we are trying to find the output by input, no? Output is across RC. So I wrote RC. Input, we have two drops. One is the emitter resistor, the other one is VB. Wherever VB is there, I asked you to write VB in terms of GM, 1 by GM. And emitter resistor, we have to divide by alpha. Or if you want Kirchhoff's voltage law, we can do it. V0 equal to minus IC into RC. This is a ground, no? This is IC. Vin or Vs is IE into RS plus VB minus.
Yes, sir.
So now you do V0 by Vs.
Yeah, got it, sir. Yeah, got it. Actually, I missed this space, sir, because of the network.
Yeah. Good.
Hello, sir.
Yes.
Sir, can you please explain once for Rule 6?
Rule 6.
Yes, sir. 31.
1, 2, 3, 4. Acha, what we are going to do tomorrow, right?
Sir, you took last to know that.
Yeah. Last one. 1 plus GMR naught, we have to multiply. The rule 6, I will draw it here. Yeah. See, tomorrow we are going to do problems on this. Whenever there is a MOSFET or a transistor. Now, this is like two resistors in series, no? You have R0 and two resistors in series. Generally, if you have two resistors in series, what do? We will add them. We will add them to find the equivalent resistance. But here, the currents are different. Here, are you getting? There will be collector current, there will be emitter current, and there are dependent sources and all that. So that is why I found that if you go from collector to emitter or drain to source, this resistance should be multiplied by a factor K, by some factor K. What is that value of factor K? I found it to be 1 plus GMR naught. 1 plus GMR naught. Are you getting?
Yes, sir.
So this actually they are in series. We have to add, but it's not like a simple resistor. No, this is a dependent source. So there is some GM factor coming into picture, R0. So 1 plus GM R0 is that extra factor we are going to multiply.
Okay.
And I told you in a cascode amplifier, if you keep on connecting transistors one above the other, the output resistance will increase. It is only because of this 1 plus GM R0, 1 plus GM R0, 1 plus GM R0. You keep on multiplying and you pile up transistors like this, the output resistance will keep on increasing and early effect we can eliminate.
Oh, yesterday, sir, you ended with that thing, no, sir? Then
Yesterday?
yesterday's class last you draw one figure, no, sir?
Yesterday class last.
No.
Oh,
the same
yesterday, no?
concept you-
My mind is
Yes,
not
sir.
working. Yeah, tell me, what is the diagram?
Sir, no, sir. One transistor connected, cascoded and connected. That time you said the same, no, sir. That is-
Yes, same thing I told. If, yeah, you're right. If you connect in cascode, one above the other, the output resistance increases and slope is 1 by resistance. So resistance increases, slope will decrease. Early effect we can eliminate.
Yes, sir. Thank you.
Yeah.
Hello, sir.
Yes.
Sir, I have a small doubt in representation, sir. Sir, we have a nonlinear equation IC equal to IS into e power VB by VT.
Okay.
That V is smaller capital, sir.
See here. IC, capital I, small c is IS into e power capital V, small b, small e.
By VT.
Now, this is nothing but total instantaneous value. This is total. This is also total.
Yes, sir.
Okay. Total. Now you want to write only DC. Then capital I, capital C is IS into e power capital BB by VT. You can write. This is for DC analysis. This is for the total instantaneous analysis.
Sir, 23F, sir. 23F.
23F. Yeah.
Sir, between the base and emitter, you are representing capital V and small b, but in while writing
this one is small only.
Small only, yeah, sir.
Yeah, my handwriting is big.
Sir, I'm actually in confusion that what is small v and capital.
No. All AC analysis small VB.
Small v.
Yeah.
Yes, sir. Thank you, sir.
Okay.
Hello, sir.
Yes.
Sir, 28F.
Yeah.
Sir, here how you replace transistor with Thevenin equivalent, sir?
Yeah, first I had a transistor. Thevenin equivalent means it is a voltage between the 2 points. Are you getting?
Yes, sir.
In series with resistance. So
Yes, sir.
we already know that the output at emitter follows input at base. Yes or no? So your VTH or the open circuited voltage will be fully Vin. In open circuit, what will happen? Okay. Even if you take a drop here, first of all, there is no current flow here. Yes or no?
Yes, sir.
When I open circuit, so complete Vin will appear here. That is V Thevenin. What is R Thevenin? You are seeing through emitter. That means alpha by GM is the resistance. So I replaced transistor by a voltage source V in series with alpha by GM.
Sir, we can do like that also. I mean,
Wherever.
replacing of transistor with Thevenin.
Yeah, and then you can do by simple voltage division, no?
Sir, that is okay, but replacing of transistor with Thevenin, that I have doubts.
Yeah, that's what. Thevenin means what? A voltage source in series with resistance, no?
Okay.
Which one do you have? These are all dependent sources. You can replace them. No, what is your doubt?
Here it's not.
No, do you say that not replace?
Sir, actually my. Sir, we should not replace. I heard of.
Why we should not replace by Thevenin equivalent? Because we are applying small signal, no? When we are applying small signal, can't we follow Thevenin, Norton? Acha, we have already done BJT with Norton equivalent, no? GM VGS in parallel with R0, GM VB in parallel with R0. That is Norton equivalent only. What is a small signal model? Is it not Norton equivalent?
I say.
Then any Norton can be converted into Thevenin, no?
Okay. Sir, one more doubt.
Yeah.
Sir, in 37.
Hello?
Hello, sir, 37 slide.
37.
Yes, sir.
Daddy.
Yeah, tell me.
36, I think.
Yes.
What?
36.
Yeah.
In AC analysis, Sir, here in AC analysis, we have shorted, no, sir, that VCC. Then how we get VCC R2 by R1 plus R2?
DC analysis, it is open circuit. So it is VCC R2 by R1 plus R2. AC analysis, it is short circuit. So it is V in. So what is the total voltage here? The total voltage I am telling you, when you apply a signal, the total voltage is, the total voltage at this point is VCC R2 by R1 plus R2 plus V in.
Okay.
Class done.
Are you getting?
I said that is okay. And 38, sir. 38.
38.
Class done.
Just a moment. Give me chocolate. Yeah, 38. Tell me.
Sir, actually, it is in series when current will be same, no, sir.
What?
Have you wrote like R0
1 plus GM R0 I have proved, no? There is a, it is not just a current, there are dependent sources also, no?
I mean, if we have beta larger than IC and IE are same, no, sir. So we can take directly R plus R0, no, sir.
Yeah, we can take, but first of all, this is this R0 is the dynamic resistance, the Norton equivalent of the current source, no? There will be some amount of current flowing here. Because of that, you get an extra factor.
I didn't understand, sir. 1 second, please.
No. A transistor is not resistor. If it is resistor means we can simply write this R0 and this R in series. But in parallel to it, there is one GM into VB, GM into VGS. What will you do to that current source?
Hello, sir.
Yes.
Sir, can you please again explain that rule number 6? I didn't understand that rule 6.
This rule,
Yes, sir.
yeah. See, this rule number 6, I have already proved, no? Which paper is that?
Sir, 31F, sir.
Yeah, here.
Yes, sir. Yeah.
Can you see here?
Yes,
Yes,
sir. Yes, sir. Yes.
So this is the MOSFET or the BJT, whatever. For this, I am connecting a resistor here. So it is not R0. You have a voltage source also, GM R0, V pi, and then there is an R. When I do V by I, I am getting this extra factor 1 plus GM R0, I am saying.
In BJT, it is different, sir. R0 is in parallel, so that's why.
In BJT, it is R0 plus 1 plus GM R0, and then you have to take R parallel with R pi. This extra R parallel with R pi. Can you see here?
Okay, sir. Got it, sir. Thank you.
Yeah. Tomorrow we will do problems on this. 1 plus GM R0, you remember the factor for tomorrow's class.
Okay, sir. Thank you, sir.
Okay. Yes, anybody else? That's it?
Hello, sir.
Yeah.
Hello, sir. 31F, sir. Differential amplifier.
Yeah.
Sir, here you are give V into the Q1 and you are taking the V naught at the Q1, no, sir.
Yeah.
If we want to take the output at Q2, then how do we solve this problem?
Positive we will get. Instead of minus GMRC by 2, you are going to get plus GMRC by 2. I will explain in differential amplifier.
Okay, sir. Page number 10F, sir.
Yeah.
Sir, in the second the fourth one, sir. Next page, I think. Fourth problem.
Yeah. Fourth,
Sir,
this is
actually,
rule 3, no?
sir, in that only I have. Sir,
Yeah.
here when we are seeing through the base, we are replacing the transistor with R pi, no, sir.
R pi, yes. And then there is a resistor at
First,
emitter.
sir, first, can we replace the transistor with R pi and in
Yeah, we can
in
replace like
series we
this.
should add R.
We can replace R pi and then we have a resistor Re. Now here there is IB, here there is beta IB. So this current is going to be 1 plus beta times of IB into Re. And here you are applying VL. This is your IB. So when you take KVL in this loop, your V in by IB is going to be R pi plus 1 plus beta times of Re.
Okay, sir. Actually, I want to replace the whole transistor with R pi and then by series R pi plus Re, like that we should get.
Yeah. I mean, if same currents are flowing, yes, we can do it. In R pi, base current is flowing. In Re, emitter current is flowing, no?
Yes.
So if you imagine a single base current, the emitter current is actually 1 plus beta times of base current. So that factor 1 plus beta, if you multiply through Re, then what you said is correct. Now you can say that in base current there is IB, emitter also there is IB. Base current is IB, emitter also there is IB, but resistor value has changed to 1 plus beta times of Re.
Okay, sir.
Are you getting?
Okay. Yes, sir. Yes.
Yeah.
Thank you, sir.
Yeah.
Hello, sir.
Yes.
Sir, in previous day you said that in cascade current source, the resistance, sorry, the current in variable resistance is same, no, sir, like IC is equal to IC.
Yeah.
That is due to because of cascading or large beta value, sir. On what reason?
No. See, in a series circuit, only one current should flow. That current is because of that 1 volt and that resistor.
Okay.
But underneath there is a 1 volt source, 1 volt drop no across resistor.
Yes, sir.
According to Ohm's law, I equal to V by R.
Yes, sir.
So that 1 volt will be so stable there because your VCE, VCB and VB are fixed for lower transistor.
Yes, sir.
So that is why the current is constant. And in series circuit, same current should flow. The same constant current will flow through upper transistor also.
Okay.
Are you getting?
Sir, once can you draw and explain, sir, that one?
This one, no. Here we have a transistor and this voltage is 1 volt and 1 K. Current is 1 milli.
Yes.
Same current will flow for any section. This is a load section. Load section. Now, why there is no early effect? This is constant, this is constant, and this is constant. So same current will flow through the load. In this load, what you want to connect? In this load, you can connect whatever you want. You can have another resistor and another transistor also, no problem. So here voltages will changes, but IC will not change because this whole is going to act like load, constant here.
Okay, it is not based on beta, sir.
Based on beta, no, same current will flow, no. Acha, here base current is also there, you are saying. Okay, you imagine MOSFET, what is there? No current is there, gate current. If this voltage is 1 volt, same current will flow, no?
I understood.
What?
I understood, sir. Thank you.
Yeah, good.
Hello, sir.
Yes.
Sir, can you go to 16F?
16F.
Yes, sir.
Yeah.
60. Sir, when there is a resistor at emitter, we need to multiply by 1 plus beta into alpha by gm. Yes, sir.
If there is a resistor,
Emitter terminal, we have to multiply 1 plus beta into alpha by gm.
yeah, if you are seeing through base,
Yes, sir. If we are seeing from emitter, if there is a resistor at base, we need to divide
divide.
beta, r pi by 1 plus beta, right?
Yeah, yeah.
Sir, if both resistors are there, sir.
But where you are seeing,
Oh, yes, sir.
if you are seeing through base, already same current is flowing. RB plus R pi plus 1 plus beta times of RE.
Yes, sir. Okay,
If you are
sir.
seeing through emitter, it is alpha by GM plus RB divided by 1 plus beta.
Plus beta. Yes.
Okay.
Okay, sir.
Yes, Sanjeev Krishnan. Is that all? There's some Sanjeev Krishnan raising his hand. Anupama Reddy, Sanjeev Krishnan.
Where is it, Dharma Krishna?
Yeah, I think it's done. Okay, then we'll stop for today.